Gavin would like us to. Right. Do you want to wait 5 minutes, Gavin, or you want to? It's okay to go. Yeah, because we're worried about I think we want to get everybody riled up. We'll probably have some people come in from their lunches as we start up. Thank you all for coming back. We had an interesting morning session. I've been thinking about Jeffrey's speech. That was quite an interesting dialogue from start to finish on what our problems are and how we frame them. I'm very excited to be here with our panel today, and I'll introduce everybody in time. We'll have some short presentations followed by some dialogue, hopefully. One of the things that we have been talking about as a panel is I guess, getting into this idea of incremental shift, what David had started out with, this idea between paradigm and increment, paradigm being maybe the solution to everybody's problems of a wonderful renewable energy resource that makes all of these things go away for us, but we sort of know that that's maybe in research, but not happening right now. The incremental part, of course, is what we deal with every day. And I'm an engineer. I deal with a lot of different projects from city scale to building scale. And I think we are in a very different time in terms of redefining how energy use in buildings and building design happens. And I would want to put some things on the table here for our discussion afterwards, but also in framing the speakers in terms of thinking about energy as a resource, as a finite resource, but how we deal with energy in the design process, particularly around buildings. Juan will speak about some of the architecture that he's doing in terms of process. Toni will speak about some of the ways that we're rethinking educational process around design for energy. And finally, about policy, and Janette thinking about ways of really interpreting energy. This is all in the incremental area now, because as a finite element, as a finite resource, we need to think of energy in terms of its performance. How do we get more economic productivity out of every unit of energy that we use? That is part of the problem. That is part of the defining the solution, as Jeffrey started off with. So I'd like to introduce Juan Herreros to begin with. Juan is an architect from Madrid, teaches at the University of Madrid as well as at Columbia University. He has some very interesting projects to show us. He's been in practice since, you said, the mid-'80s, and two recent projects, one, the International Convention Center in Bogota, and also the Edvard Munch Museum in Oslo. I'd like you all to welcome Juan Herreros.
Good evening. Thank you very much. It's a great pleasure to be here. And now that I'm here and I have spent the whole morning, I can't imagine not being here. So I understand that I've been invited because my architectural practice, and at the same time I have been compressed to do this a little bit faster than thought. But so I want to go straight to the first idea. So from the architectural design world, energy seems to be related to installations and mechanical systems of buildings. I think this is an old association. I think a lot of people today, we see energy as the real big concept that can integrate all the specialities working in the design process. So energy can be really like the common ground or the common culture. So in this way, energy is the opportunity to break this idea that the architectural project is done like the sum of independent chapters signed by independent specialists, or expertisms. So the question is, how can we integrate these specialities? How can we really change the way we work and the way we design, understanding that all these people have to be from scratch at the same table in the beginning. You can't read this. It's not very important. But this is the diagram of the whole people participating in what I call a middle-class architectural project. Middle class is 90% of the projects, all we do in our offices, no? It's like middle scale, middle budget, middle technology accessible, middle parameters of comfort. So it's in Colombia, it's in Bogota, and it's a middle-sized Congress Center. We have seen in the last year a lot of examples of architects doing very simple things in emerging countries with very, very modest resources. Something that is interesting, and we have developed a kind of indulgence toward these examples. On the other hand, or in the other extreme, we have been also fascinated by the work of those with unlimited resources and extraordinary consultants concerned with making big statements, usually too expensive to find an intelligent use of energy. I think in between these two extremes, most of the architectural practice is content. No? So here, where I'm interested is about talking these normal buildings, this project that we do every day. No? These first cases are interesting. I'm talking about the very, very modest ones, and you have in your mind a lot of these examples, because they show us how much can be done with very little. The second group can be shown like the laboratory where new technologies or new advantages can be essayed and transport to the common architecture, like Formula One is letting every car to have an airbag. No? But at the end, we have the impression that in these middle-class buildings is where the architecture has the opportunities to do some steps ahead and to make some deep reflections about what we do, what we want to have, what we are going to call quality or comfort. How can we do something accessible to many and understandable by everybody? So I would like to draw attention to how much we need to implement an ambitious rationalization of our methods of working, how to get this balance between complexity, cost, and profits is not so clear that we can get it if we continue working as we have been done. In this diagram we have seen before, the architect is not in the central part of the diagram. No? It's exactly there. No? So we are going out of this traditional image of the architect like the conductor of the orchestra, something that I really hate. No? And this is trying, this map, to show how the process of design is the process of creating a kind of ecosystem inhabited by all these different people looking for the integration and balance in the same way that the building they are trying to design wants to be an ecosystem which is seeking to balance its biological equations. So I think that as we work in the closest way in our offices than the buildings are built, for example, we will do a big step in this direction. So this is crucial, how complex we want to be, how negotiate all the components of complexity that many times is full of contradiction in architectural design and also full of superficial ingredients. In this case, after this concept easy to understand, and this section, we can see how the big spans of the big rooms that we need in a Congress Center are creating a new dimensions, are creating a lot of volume that can be used for moving the air. And we have now here a very interesting discussion between local consultants and international ones. We are here attending how the locals really want to make it easy. They want to make it quite simple. And they are, in the cases the architecture is not getting the quality enough, they are asking us, they are asking the architects to change, to reorganize the design to reduce the energy impact. The big name consultants that we are working at the same time here, they are asking for more complicated solutions. They are asking for a lot of machines and a lot of mechanical systems that the locals want to avoid. This discussion is quite interesting because at the end, the discussion is a cultural one about the parameters of comfort that the local people is ready to accept, and the international consultants are are explaining that the international public are the Americans, no, will not accept these comfort parameters when they come to the Congress Center to attend the congresses. So this is interesting because based on the number of studies carried out about the relation between comfort and productivity that basically take humidity and temperature as if they were all, we have seen in the last years a vertiginous growth of facilities and increasingly rigorous regulations, and why not talking about the LEED label and all these things which are rising the budget of our projects in a daily basis. And once again, the problem is how complex or how complicated we want to do this. How are we ready, how much we are ready to accept that questions like comfort are a cultural issue. So I was talking about this large span required for the floor slabs and how it brings an enormous amount of space useful to move the natural ventilation. So this is a building without any machine. It's 300,000 square feet over the ground zero, and it's not machines at all. We are moving the air through these slabs. So we take these 4 columns for all the supplies, and we have these slabs empty to take out air from the outside and move inside. So this is another reflection about how architecture changes its dimensions to have a more efficient dialogue with the questions of energy, in this case to a kind of low-profile energy. So all the architectural decisions and all the strange architectural dimensions that we have here are based in this process. No? This is the drawing of the architect trying to understand how it works. This is the drawing of the engineers explaining and revealing how we are working with very simple elements. And this is a configuration of these elements, completely accessible, which can create a kind of complexity, but the complexity is not coming from the use of very, very advanced technology, but the reorganization of the conventional construction elements, constructive elements in the building. No? So this is a new floor appearing. It's the floor inside the ceilings. It's the floor of these huge cameras moving the air thanks to the difference of temperature between the different facades. No? And in the heads of these slabs, the air will be introduced. This is a picture of one of the animations, no? When we see the air coming into and going out with these chimneys. This is one of the photos of the animation. I could show you, but we don't have time enough, explaining how the relation between the temperature and the temperature of the air and how the air is being moved to go out. This is the big auditorium with its own evacuations of the air. Some architectural elements like chimneys appear on the roof, so are also giving some opportunities of designing. And the facade is transformed by in this way into a super, I think, different approach to the one we usually have when we compose a facade, when we do the design of this element. So we have, some points where the air is coming in. We have very different translucencies and transparencies depending on the use of the room behind. We have very different deepness also of the architectural elements. And because the climate conditions of Bogota, with very cold mornings and very hot evenings, these facades also have grown in the thickness you see here, how big they are. So this is perhaps a step ahead after the facade that of the layers, saying, okay, we have been building curtain walls for 40 years, and after that, the problems of the curtain wall are solving, keeping the curtain wall, but adding some layers in front of, like lamellas or solar protections or whatever. Here, I think the concept is different. The concept is that the facade itself is a three-dimensional element, so it's a super architectural, tectonic piece in the building, incorporating some of this system, but sometimes having also two glasses separated by 1 meter, so creating an interesting superimposition of different equations, like acoustics, light, protections, and temperature, humidity, condensation, etc. And that means that every facade has to be studied carefully. This is the fourth one. It's quite interesting, this weather of Bogota. And we started with some very simple interpretations of the conclusions. We really wanted to do something quite simple with the incorporation of very singular elements to create this piece that is working absolutely engaged with these structural installations, facade, and natural ventilation system. So I think this is interesting because we have been working for years in the idea that the mullions should be as thin as possible, glass surface should be as flat as possible, everything should be light and translucent or transparent, and looking for a concept of ingravity. But today, I think we are really changing these aesthetic conditions, and we are discovering that, for example, in this case, double glassing is not the best solution. Most of the building is solved with single glass. That the thin facades are not working so well, but even the different layers too. So we have to go into this other direction. And we have robust mullions, something that apparently could be not very interesting years ago. So this myth of technological progress, like double glassing or air conditioning, are becoming a matter of deep discussion. I want to show very fast this other example. This is the Museum for Edvard Munch in Oslo. This museum is organized in two different buildings. One is the museum itself. It's a concrete, solid, robust building. So these are basically the rooms for the art. And this is the communication system, which is like a vertical public space going up. So we have two different buildings with two different architectures, with two different spatial conceptions, and two different energetic systems. So this is the contrast between these rooms of the concrete massive building and the lighter communication we call dynamic museum. So this is, I'm missing something. Okay. Now this is just the expression of this program with this vertical piece of steel structure and the vertical piece of the concrete structure with nearly 20 meters of free span. So we have heavy concrete slabs and heavy walls. Of course, we are in Norway. We have super thick isolations. But this is the most interesting. We have the concrete building is heated and cooled through the geothermal energy at the bottom of the fjord, having water or hot or cold water circulating inside the concrete. This is what is called CABS, thermal active building system. So it's working like a passive element, receiving this water and transforming the whole massive inertia of the concrete in a machine. It's like putting the building to work, no? So it's a really interactive, no? The ventilation of these rooms is having out some of this air into the dynamic part. The dynamic part is less exigent, so this air is naturally ventilated through the top. So we have two completely different systems, but the two systems are at the same time working together, no? This is just going very fast. This is the lobby. The roof of the lobby, or the ceiling of the lobby is a three-dimensional slab again, because we can't have machines on the underground, into the water. So we have them here. So the building itself is not putting all the machines on the basement. It's not saying the machines are refused to a place where architecture is not working. They are here. They are part of the building, and they are quite present. You know? The ventilation system, which is a separated system in every floor, is also having a strong presence. So we are having this organization in 2 rooms every floor, thanks to the presence of this ingredient. No? We need big volumes because we are moving air very slowly. It's the case of Bogota. So we are again going against the idea of doing it very simple, light, and thin. No? So the facade again is trying to be quite active, but at the same time quite simple through this geometry that can take all the energy from the sun in the different positions. Norway is a difficult place for sun, but there are a lot of sunny days. And this is again the diagram of this project. No? I think just to finish that the non-residential buildings are needing 5 times more of energy than the residential ones. This is quite important because how many office buildings we know that are giving to the architectural culture some progress in intellectual, aesthetic, or real interesting terms to justify these 5 times of energy is just because the spectacle is just to be expensive enough or to show the potence of the companies. A few years ago, we were concerned about our buildings consuming a lot of energy. Now we are trying to do buildings not consuming, having a kind of zero balance like these ones. Perhaps in the future, we will be able of making buildings like produce energy, produce storage, transport, distribute, consume, and recycle energy. So in the meantime, we have to find another way of thinking. Instead of doing the same at a lower cost, we should be thinking, and I think that's what we are doing here today, thinking differently, outlining a new agenda. Because there are many people researching about new resources of unlimited energy in the idea that if they get that, we don't have to change, no? That could be a real problem, especially for architecture, for the progress of architecture, because if that happens, we really will lose a great opportunity of taking seriously an agenda that is not only based on the scarcity of energy, that is a new paradigm about how complex is the world we want to inhabit. Of course, the university is the place, the #1 place to do that, and the kind of training we give to our students is the great topic, as David Benjamin was mentioning now. At least, just to finish, we have 3 initial steps that for me are extremely clear and perhaps apparently very obvious, namely, build only what is necessary, make it easy, and do not gratuitously destroy. I would like to have 5 minutes to talk about how important will be in the next future to recycling the existing buildings and how attractive and could be that for the invention of new typologies based on the idea of adapting different programs to existing buildings in a kind of new complexity. No? But this is the same that John Wayne expressed sometime in his famous quote, "Talk low, talk slow, and don't say too much." Okay, thank you very much.
Great. Thank you, Juan. I think that's interesting as we get into energy as a finite resource, how we manage it through the design process, and how we manage it culturally through vastly different media here, in terms of the very technical to the very simple. Our next speaker is Janette Kim. She is the Director of Applied Research and Practice at Columbia University, as well as a principal, all of the above, and also Director of the Urban Landscape Lab at Columbia. And I think in terms of thinking, our conversations between Janette and I have been about the nature of understanding efficiency and energy, and I think she has some very interesting things to say about that. So thank you, Janette.
Hi, everyone. It's great to be here. I'm excited to be part of the conversation. I think today I would like to present to you a project that I've been doing at the Urban Landscape Lab. Let's see, figure out how to use this. I think it should be a forward arrow. Oh, right. Makes a lot of sense. Thank you. Great. So the project is called the Underdome Guide, and it's a research project that I've been doing with the designer and historian named Eric Carver. My hope is that this project will help bring to the discussion today a context of a kind of scale of public interest and what that would mean for energy. So the project is an online guide and soon a book that acts as a kind of architect's voter guide to energy. And the idea is to recognize that we do have a set of very active debates about energy, meaning that, and basically we're interested in the idea of debate, both to recognize that we have a kind of pressing need or a very, very urgent need to address the kind of crises that Jeffrey Sachs carefully laid out for us. But we also have a very pressing need to not sort of jump to conclusions or jump to a sense of agreement that would, I guess, push us beyond what the contentions or the debates behind energy actually provide. So I see the debate as a useful starting point for discussion. So what you see here is the homepage of our website, and the site basically maps out a spectrum of sometimes contending, sometimes affiliated positions on energy. What we do is we ask how each of these approaches often have implicit narratives about governance, political representation, lifestyle, cultural norms, and images of the city that often get smuggled into play when we talk about, that get smuggled into play in the name of energy savings. So we've organized the map around 4 major topics: power, which looks at governance; territory, which looks at the changing contemporary city; lifestyle, which looks at questions of comfort and basically just living; and risk, which asks how we work collectively to anticipate uncertain futures. So ultimately, the map is kind of a Mad Max-style stage for debate. Within each topic, each agenda is drawn out as its corresponding physical environment. It's a little hard to see right now, but each position or attitude is drawn as a kind of biodome, imagining that we as architects are always producing different kinds of biodomes in the city. So if you click on any of the domes from our homepage, you will see a kind of database page that demonstrates arguments for and against this agenda. And a lot of the discussions are also coming from a series of panel discussions that we held at Studio X, which in many ways have influenced what I'm talking about today. So I think just to position this, the reason why I'm talking about this project in this context, I think I'm very happy that Craig has basically challenged us to question and rethink what we mean when we talk about energy efficiency in particular. And I think in this regard, it's important to distinguish between energy efficiency, let's say, from other efforts such as reductions in gross energy consumption, so just using less, or on the other hand, a search for better fuels. And I think in distinction from those approaches, energy efficiency in particular basically gauges energy consumption and energy savings always in relationship to other values, so profits, cost, comfort, productivity, and so on. So in other words, with efficiency, we are talking about minimizing losses and maximizing gains. And in that sense, energy efficiency is always a question of, it's always a relative question. The question is, what are we trying to gain? What do we value, in response to the things, in response to losses? So as a basic resource and a basic need, then, energy basically draws forward much broader questions of public life than we often recognize. In addition to discussing dollars saved, watts conserved, what about measures of equity, access, happiness, comfort, and risk? So my goal this afternoon is to try to identify some broader measures of energy performance and draw them into the conversation. I'll just describe a couple of the agendas that we've mapped out in our kind of database. And this corresponding sites, buildings, technologies, and kind of physical environments that accompany them in hopes of demonstrating this broader set of interests. So I'll go through today two of the topics, power and risk, that I think most sort of directly address this question of how we measure value. And starting with power, basically what we've done is we've organized, so if each of these are kind of attitudes, positions on energy, we've organized them across a kind of, let's say, a structuralist grid, or maybe better yet, a kind of a graph that's similar to the approval matrix in the back of New York Magazine, that you would basically see kind of attitudes organized along the spectrum of, let's say, a free market to a kind of more socialized or collectivized model, and then from an individual to a top-down strategy. So in many cases, we're looking at, sorry, I forgot to introduce the topic of power, but with the topic of power, we're basically asking how we get things done, who's involved in the process, who can be effective, and how do we understand the relationship between government, corporations, organizations, and individuals in this kind of broad question of how we get stuff done. So let's start first by looking at the Bank of America building, which in many cases can be a kind of showcase, as well as perhaps a target of discussion. And we've kind of categorized this as a kind of an example of a kind of high competitive model. It's this idea that the free market would yield big investments, big changes, provoke others to follow suit, and in some ways really have a significant impact. And I think here the question of building envelope does come into play, that the project is a kind of green billboard. Like, it itself is this gleaming image, this kind of gleaming symbol of a cutting edge, kind of platinum standard that is meant to kind of boost the reputation of Bank of America and attract desirable tenants to the Durst Corporation. And in this way, I think one can see this kind of ambitious desire to produce change. At the same time, the trade-offs are similarly illuminating. A Durst Corporation representative, for example, acknowledged that, yes, a solid facade would actually be much more efficient, but that the glass, the kind of all glass enclosure was worth it to garner market rate rents, that it was worth it for the corporation, for Bank of America, for example, to locate their offices along the glass wall, despite the architect's suggestion, precisely because these offices would limit daylighting into the center of the offices. So these moves were less energy efficient, but worth it to the owners, and in their eyes, allowed them to basically invest, like that this was the reason that they could invest in high performance systems. This was the reason why they could invest in a cogeneration plant within the building. Skipping to a completely different scale and a completely different measure, or a kind of measure of success, we could look at the Federal Weatherization Assistance Program, which is a federal program created in 1976 and then more or less revived by the stimulus bill several years ago. And according to this program, federal dollars go towards weatherizing the home of low-income residents. Sometimes in public housing projects, sometimes supporting tenants living in low-income housing, essentially market rate but low-income housing. And here I think we see a completely different set of standards, a completely different set of metrics, that here the highest goal is to reach the greatest number of people, to reach those who can't afford to upgrade, to reach tenants who don't fall under a typical model of investment, upgrades, and retrofits that an ownership model allows for. And here we see a very different architectural strategy. Far away from the glass skin of the Bank of America building, we're looking at a kind of relining of the building from the inside, this reskinning, replacing of the building's insulation, the resealing of each joint of the building, a kind of renovation from the inside out in which government is kind of on the inside. So I guess jumping to then a third very different example, we could look at Energy Hog, which is an ad campaign sponsored by the Department of Energy and Home Depot, appropriately enough, that basically encourages, I mean, we're all familiar with this, right? That encourages individual responsibility by changing the light bulbs, shutting the door, turning down the thermostat, et cetera. And what you're seeing here is a kind of image from a video game that they have on their webpage that encourages children to play this game and kind of learn how they too can play a part. So it's basically the idea being that energy efficiency is so easy, a child could do it, but that in many cases when you're talking about changing the insulation, sort of actually altering the way the building performs, we start to see some kind of holes in this argument. And I'd say that in many ways there's a kind of unspoken metric here, which has to do with investment dollars saved, meaning that we're saving money in investing in infrastructures, in more significant upgrades that go beyond the scale of what one individual can do. Taking this to a complete extreme, you could look at the example in the city of Colorado Springs. I mean, you guys might have heard this on This American Life episode, that in 2010, to address budget shortfalls, the city turned off 30% of their streetlights and basically asked individual homeowners to pay individually to turn on the streetlights in front of their homes. So we see this kind of extreme kind of neoliberal sort of defunding of infrastructures into this kind of patchwork, kind of a la carte infrastructure. And so I guess if you look at some of the examples that I've talked about so far, we can see a somewhat traditional model of the difference between, let's say, government investment, market rate investment, individual action. But I think when we talk about power and we talk about how stuff gets done, I think some of these lines get much more complicated and much more murky. And maybe this is where things just get more interesting. We could, for example, look at the way that dollar vans work as an infrastructure, that we see a kind of that this infrastructure can bring to communities transit services that are missed by discussions about rapid transit, bus networks, high-speed rail, et cetera. But here the metrics are different again. They might be different, but they're in fact no less important to cities whose growth is actually fed by immigration, for example. So here we're looking at metrics of affordability, market flexibility, the ability to respond quickly to undocumented patterns of use. Again, I guess to look at another kind of hybrid model, we could look at this other project, this other example from Denver and Brooklyn called the Living City Block. And this is a nonprofit that basically helps building owners. It's a nonprofit that helps building owners basically pool their resources together and create upgrades or changes to their buildings that can only be done at the scale of a block, let's say, or a large building. So you have the advantages of homeowners who can kind of speak up and have a kind of voice in their own planning process, at the same time that the block scale achieves certain economies of scale and allow them to kind of be able to actually afford upgrades or changes. And I think here you start to see, if we think about the Bank of America kind of skin and the weatherization interior, the kind of weatherized interiors of the WAP, I think here we see a very different kind of surface, or a very different kind of biodome, where you could look at these kind of shared rooftops that are being kind of mapped out through the Living City Block project, and we start to understand this kind of communal surface to the city. I guess as a kind of last model of a kind of hybrid approach, we could also look at the kind of mega block, the kind of new mega structure projects that we can see through the Hudson Yards development, through the public-private partnerships that the Bloomberg administration, among many others, is promoting. So I'm in a bit of trouble here, which is that I have 5 minutes left and another topic to go through, but I'll just touch on some of the issues very briefly. I want to talk about risk, which basically looks at the way that we respond to future hazards. So, in the face of disappearing resources, increasing hurricane rates, increasing forest fire rates, rising tides, and on, what kinds of risks are we willing to take on, and how do we deal with them? And I wanted to talk about this in this context because when we talk about efficiency and we talk about the metrics of performance, risk brings into account some really unusual and kind of unexpected ways of measuring these values. So for example, and I want to approach these in basically 2 ways. One is to ask, what is our appetite for risk? What hazards are we willing to face? Where do we really want to put our money? So just very quickly, we could look at, for example, a backup system for Facebook's servers, or the proposal to get rid of the dam and Hetchy and return, as a kind of retroactive preservationism, return to a landscape that was once before. We could look at genetically engineered lettuce that has been designed to grow in arid regions. Or we could look at a kind of monitoring system by the Silicon Valley Toxics Coalition that takes risks in introducing new technologies into the world, but also recognizes that we need to monitor these risks and kind of react to them in real time. So I guess the question I'm trying to ask here is, where do we want to put our money, essentially, or where do we put the value? Are we trying to back up data? Are we interested in the kind of lifespan of businesses under the threat of hazard? Are we interested in preserving landscapes? What is the time scale at which we need to preserve our water infrastructures, and so on? The last point I want to make about risk is not so much about this question of appetite for risk, but deals with this question of collectivity. And here's where we just bring in something kind of as seemingly dull as the insurance industry. This image comes from from Arups, actually just forgot their name, Resilience, Security, and Risk Consultancy team, who are looking at ways to give financial incentives to their clients to invest in better upgrades, better structures, better performing buildings, by recognizing that they will save money on insurance down the line. If you think about the performance of your building 10 years into the future, you then have a financial incentive to invest now. And I think these kinds of models start to bring into play, they start to take very seriously the kind of metrics of dollars and watts, but also recognize a much bigger kind of collective of people who are related to a construction project. What I mean by that is that you could look, for example, at the way that the Intercontinental Hotel Group, for example, designs their resort hotels to guard against hurricane exposure. So you see, for example, reef protection or emergency shelters, or like higher wind load capacities for a facade. But what about but what about recognizing that these resorts have a much bigger world than just their own structures? What about the fact that, for example, in the Yucatan Peninsula, if you see a resort along the shoreline, you also see a workers' town behind the main road that has no sewage infrastructure, no school system, no public transit system, et cetera? Is there perhaps a way to understand that risk calculations also need to take this form of response into account? Are these numbers that need to count as we kind of value the performance of these buildings? So I know that was extremely quick way to talk about risk, but I guess at least I'm hoping to bring these questions of a broader set of measures, a broader set of values into the discussion of efficiency. I think, so we talk about these other topics, territory, lifestyle, but I think overall what I want to bring to the table is this idea that we might sort of include within our own measures of efficiency ideas about access, reach, representation, a reaction to the way people really live, the way that people's movement patterns are truly happening, and a sense of a kind of collective impact that might go beyond in a scale than go further in scale than what we might typically consider. So thank you very much.
Right here. Thank you, Janette. So our final speaker in this session is Dr. Toni Kotnik. Toni is an architect and a mathematician, is currently a senior researcher at the ETH in Switzerland, the Swiss Federal Institute of Technology. We had some discussions, regarding, I think it's interesting from Juan to Janette, thinking about this idea of efficiency, how culturally this looks at design, culturally it looks at policy and other issues that affect our daily lives. I'm looking forward to hearing Toni speak about really the process of understanding how design happens and how education design happens with regards to energy. So thank you, Toni. Looking forward to your talk.
Okay, thanks, Greg, for the introduction, and also to the organizing committee for the invitation to this event, which up to now was quite interesting. And yeah, thanks also for the opportunity to now present in the next couple of minutes, hopefully with not too much technical detail, some of the basic ideas of my research at the ETH Zurich. And before I start, maybe in general, the research we're doing there is kind of concerned with the exploration of methods of how to integrate engineering knowledge into the design process at a kind of very early stage, with the goal to, in some way, balance out the necessity of physics that there is, with the freedom of design. So with respect to energy, and I think the starting point of our research endeavor is kind of the observation that the contemporary way of living in industrialized and also in kind of evolving countries is in large part fossil fuel driven, and I think we have heard this already today several times. And with what's maybe also interesting, just to put up this number, that buildings in some way directly affect more than 40% of all energy that is consumed. If you count not only for building operation, but also include something like the energy that is consumed to manufacture and deliver building materials, or to produce infrastructure like streets and sewage systems and water systems and all these things. So with respect to these kind of numbers, it's clear that cannot be denied that built environment is somewhat responsible for a large portion of the emission of greenhouse gases, and in consequence, of course, for climate change. So I think in the current situation where we are right now, there are two strategies of how I think equal importance. How to respond to this situation, how to make our buildings more sustainable. So on one hand, of course, trying to get more clean energy, and I think that's what the panel 1 was about, I think mainly focusing on new ideas for this. But on the same side, as a second strategy of, as I said, same importance, I think it's about saving or making things more efficient, so saving energy. So, as I said, I think the question of clean energy, I cut this discussion short and say, okay, let's leave this to the engineers. Yeah, that's to large part, and I think an engineering question that now as an architect I would like to just exclude for this discussion here. But in buildings, I think the largest amount of energy that is needed for the operation, as I said, is for the operation of buildings, and this operation, of course, is influenced very much by the morphology, the kind of organization, materialization, all these questions that make kind of the building, and for which the architect is very much responsible, or at least involved in. So, and because of this, in some way, architectural decisions are kind of a crucial, I think, part and play a key role in making buildings more sustainable. And that's in some ways why our research is trying to find ways to inform the design process as early as possible, yeah, with trying to get knowledge into how to make it more efficient. I think traditionally, and also I think still in many schools and probably also offices, this informing of the design process is often based on studies of precedences like vernacular architecture. And I think these studies are very valuable, yeah, and of course they have their own rights. But if you think today about buildings, about 24-hour cycles of use, building typologies, comfort expectations, all these things that are very, very different to these former times, then it gets pretty soon clear that these vernacular solutions cannot kind of be used as some kind of blueprint how to go on. Instead, I think we have to dig a little bit deeper and look for, let's say, the basic physics or basic principles behind these vernacular solutions as a point of departure for design of contemporary buildings and energy efficient, to find energy efficient solutions. So that's somewhat how we started to look at this problem. So kind of we looked basically at the mathematics that describe some of these physical phenomena like heat transfer or things like this. And I have to admit, maybe we started this project on an evening when we had already a little bit too much wine. Yes. So we basically took a paper and just sketched out a couple of equations, collected some basic ideas. And so that's kind of the sheet you can see here. And from a technical point of view, so technical in the sense of from a point of a mathematician, let's say, these equations are kind of pretty nasty beasts, and very difficult to handle. However, if you look, however, if you look at these mathematical structures, you start to realize some kind of similarities between all these different descriptions of flows, let's say. And they all have kind of elements of conservation of energy. They have elements that describe boundary conditions. They have elements that describe the dynamic changes within these equations. And it's not even important that you can read this, yeah? It's just to understand there is some kind of formal similarity between all these things. And that of course attracts, let's say, me as mathematician, and I had to look at this a little bit more closer. And out of this kind of, let's say, mathematical similarities, there came some kind of crazy idea slowly out of it, which is basically saying, is it possible to understand kind of the basic phenomena of energy flows? And I'm really talking here of really the phenomena more and not so much of number crunching and simulations of these things. So is it possible to understand the basic behavior of such flows by using a kind of one flow as a prototypical flow and study so you can understand what flows in general do? And of course, in our case, because as maybe Greg mentioned, I'm working now in a chair of structural design, we were kind of attracted by force flow. And on one hand, as I said, because we're familiar with this, and on the other hand, this type of flow has been studied for about 400 years, so there's a lot of material around that can be looked at and probably reinterpreted from a different point of view to see if there is evidence for this kind of ideas that we had. So very soon in some way we figured out, so don't be afraid about this equation, it's just decoration, yeah? Don't. So I said we figured out very soon that maybe the basic idea we had is probably not that crazy, but problems like, for example, heat conduction in materials can be formulated by a special equation, so-called Laplacian also. And that's a kind of important type of partial differential equation. And by changing kind of the input of this function, it enables kind of modern finite element analysis software like, for example, Strand 7, to calculate various problems, for example, structural equilibrium or buckling and heat conduction, all these kind of wide field of different problems to use kind of the same solver. So basically using the same mathematical mechanism to calculate all these different problems. Yeah, this means within these softwares, more or less questions of heat and questions of forces are to some extent treated the same. Yeah, this strong interdependence of continuums mechanics and thermodynamics is not really an accident. In general, continuum mechanics deals with deformable bodies. And since part of the energy exchange takes place as heat flow, it is impossible to separate the mechanical aspects of a problem from the thermodynamic processes that are happening on the kind of level of the motion of molecules. So starting in the 1940s already, this has resulted in the reformulation of thermodynamics as a field theory in much the same way as continuum mechanics has been treated for more than 200 years. And has also resulted in kind of merging of two branches of science into what's nowadays called continuums thermomechanics. And this has led to a kind of also unifying description of a quite wide range of different research fields, or formerly different research fields, that are in some way described now by the same set of differential equations that capture, on the one hand, mechanical, but also thermodynamic behavior. And due to this kind of existence of such equations, I think it can be argued that there has to be some formal similarity in the phenomenology and of different type of flows that are captured this way. So, which means in some way our basic idea that we had seems not to be that crazy at all, and so that kind of where our research kind of got rolling in some way. I'm not going to talk now more about kind of showing more equations here, but it was just here to say, okay, that makes to some degree sense. the focus, I think, what we were then trying to do, or what we're still working on is, and at the chair or at the research group, is an attempt to make now our knowledge on force flow in somewhere operative, so that we can use it for the design process to understand maybe other types of force flow. So we're trying to experiment with these ideas. And the basic for this approach, how we're doing this, is coming from plasticity theory, so which is a kind of theory on structural behavior that's kind of, you see here on the left. And as I said, because it's in some way on a very high level in this arrangement, we would assume that whatever we catch there, the basic phenomena that we can see there for flows should be in some way also happening in other type of areas. And maybe I go through this now very quick. The point why we picked this plasticity theory is, which is maybe a very unique to the Swiss way of looking at the world of structure, is that it allows to some extent to separate questions of equilibrium, of material behavior, and kinematics, and basically focusing on just one of these effects, where in the rest of the world, let's say, which is normally based on elastic theory, there all these three effects are kind of coupled with each other, and it's a kind of whole mess. Yeah? And so just to give maybe a quick flavor, or to boil it down now, this kind of theoretical framework to the normal life of an architect. The interesting thing with this theory is now that, in some way, based on one of these theorems, you can, in some way, reduce the question of flow to some degree on questions of equilibrium, and they can be modeled by a very simple system of these, call it strut and tie solution, which is kind of related, as you can see in this drawing on the right, in some way as emerging as a resultant forces of the underlying stress fields. But as I said, it's not so important to understand. The more important is, how does it work now for an architect, or how can you use it? So the basic, or the first thing, which maybe comes as a surprise for many people who had some kind of structure courses, is this whole thing lives only with compression and tension. There is no moments. Now forget about this. And so it's just very intuitive. Everyone understands how compression tension works. And then within this, what we did is in some way translating now typical questions of structure into some kind of geometric description. So these questions of equilibrium, like, okay, forces have to add up to zero, and basically means that these forces form this kind of circle, and also the action of forces, all the lines of action, they have to intersect in one point. Yeah, all these things mean basically what you probably know from your own lectures is analytically can be described with these kind of typical things, like sum of forces in x and y direction is zero, and sum of moments is zero, and all these things. Yeah. So basically, it's a kind of geometric set of rules that allow now to construct kind of the flow with very simple operations that are very close to what architects normally use anyway, maybe to construct a floor plan. It's very simple operations. What's interesting now is that you get, of course, a very close relationship between the forces and the form, so that you get kind of information on how form emerges out of this flow. So it makes it in some way visible. the most important thing here to understand or to get as a message is actually that what you see within this framework very easily is that you as designer can start to redirect the forces or the flow of forces in space. So it's not, let's say, the physics that describes exactly where things are going, but physics works as a kind of very soft framework which you as designers start to kind of mold in some way. So you can redirect the forces in space like you want to do it. Yeah, like you can see here in this classic example of a frame. Looking at this kind of frame corner maybe a little more in detail, and that's now where we get closer to energy, is if you in some way naively now add to this kind of directions of compression and tension also some kind of arrow so you can see in which direction the forces move, then you can think basically of this redirecting of forces as something like flowing around an obstacle. And as you can see with these arrows, they are now there in some way a kind of pattern emerges, like a turbulence pattern that you might know in a very similar way from other type of flows, where, for example, wind tries to move around a house with very similar kind of phenomenology of these kind of turbulence patterns as a way of dissipating energy. So, yeah, this was a kind of very long introduction to basically say it seems that the method has some potential to to understand a little bit better how some kind of flows of energy through space that are driven through thermodynamic rules happen and how to maybe redirect them and work with them. So the important thing here is now for me as architect and also then for people or students who are working with this is not, as I said, to simulate flows of energy, whatever, of heat or whatever they want to work with this method in precision. That's not going to work. But what is provided through this kind of approach is some kind of, call it diagrams, abstract diagrams that can help the architect to incorporate simple geometric construction that give information about the flow within the structure to guide the design in some kind of direction. So it's more like a diagrammatic machine that we're trying to produce. And to leave it not so abstract, maybe here a quick example of a competition entry for a courtyard development in a kind of urban area in the Karameikos district in Athens, where it's a kind of typical residential block with some leftover space, a courtyard space that, of course, never used, especially not in summer because it's too hot, and also kind of the whole social activities are basically orient outwards to the street. So what we were trying to do is in some way activate this space within as a kind of way to bring define a new social space to connect these people in this area or in this urban block closer together. And luckily, in some way, we had as a kind of context, or if you want to call it part of the genus loci, that the prevailing winds in some way were coming out of a direction that more or less was kind of hitting into this kind of opening. So the basic idea was, can we kind of redirect the wind to use it as a kind of, to produce some kind of cooling effect for this courtyard? And I said here, using these ideas of flow from our structural knowledge to in some way produce something like abstract diagrams or ideas about how flow behave and how we can modify it. And here as an example, how it evolved that that through that type of opening that you have in such a plate, you can not only redirect, of course, the flow, but you also redirect you change the intensity of the flow. And using this, as I said, as a kind of abstract diagram, we were then working with this kind of mechanisms to form something like a collection of holes, if you want to call it. So it's a kind of set of fins that was in some way redirecting the wind, taking it from the higher level down onto the ground level, at the same time through the redirection and compression, changing the wind speed and then taking it around into the courtyard. And at the same time, these kind of fins slowly changing into benches and then here into larger or smaller kind of buildings like a kindergarten and a bistro. So there's a kind of seamless transition from a purely kind of functional element at the wall into some kind of space that is then used for people. And we later then also kind of did some serious calculations and simulation. Then luckily it turned out it seems all to kind of work. It all goes in this direction that we proposed. And we did also some wind tunnel tests, and also there I think they kind of showed that it's not totally wrong what we did there. So to wrap it up, just to get to an end, is what are we trying to do in our research is, of course, on one hand now to try to transfer all our knowledge and intuition that we have from kind of force flow into an understanding of other types of flows. And this means, of course, now looking much more into detail, on one hand, into the mathematics behind, so really rigorous proof what is the scope of this method, what is true, where it goes totally wrong, and to understand better how it works. But then on the other hand, that's probably the point one is more the boring bit that has to be done. But maybe the part two is then really to explore the potential of this approach within design competitions, projects with students on different scales, what we have already done to see how we can handle kind of this method, and does it really help to maybe rethink how sustainable architecture could look like today. And as maybe just to introduce maybe a topic into this now following discussion, is the whole thing that we're doing here is basically aiming at the question, how can we change the way of communication between different specialists that are normally part of the design process, where in many cases we have, for example, engineers and the architect, both specialists, and we have this kind of loop of information where it goes between these specialists forward and backward. But to some extent, I would argue that this kind of typical communication situation is working only in the way that it produces in some way always negative feedback. It just tells you get information from the specialist what doesn't work. But normally you don't get really a good guidance back, because let's say often an engineer doesn't know enough about architecture and vice versa, so they cannot really inform them on this with their kind of specialized knowledge, often in a good way. So what we're trying to do in some ways, boil down the whole thing on simplify the approach on such a level that we have a kind of common knowledge, which then is the starting point for discussion. So this kind of simplification is in some way an attempt to allow a real discussion that is much more productive than the typical way of communication. So that's kind of what we're trying to do in some way. And I guess I leave it at this point.
Thank you, Toni. I think we are running a little bit behind here, and we'll probably go right into the next panel and save questions and comment for afterwards, because we have a hard stop at 5 o'clock today. And there'll be a break after the next panel, but I'd like to introduce Scott and to come up and introduce the next panel of speakers. Okay?
So I think what we'll do is we'll have kind of a mega panel discussion at the end of this panel and bring everybody up so that we can get a chance to get Q&As for everyone. So this is the third panel before we go into our keynote. And just as a brief introduction, in 2008, The Economist, the magazine, dedicated a special issue to the very topic of this conference, the future of energy. And they presented really a pretty optimistic forecast for alternative sources of energy and new technologies that would lead to, a world less dependent on fossil fuels. However, the authors also warned that past efforts to develop and popularize these technologies had not been very successful. And there are many reasons for that, including just the kind of economic and political momentum and the relatively low cost of fossil fuels. But they also said it was a failure of imagination by researchers, by entrepreneurs, by the general public to envision viable scenarios for the adaptation of these alternative sources and also for new patterns of consumption. So I think that this is changing. I mean, I think this is something that probably has to change, and we even see it in the presentations this morning that it is changing. And it's changing with the confluence of a couple of things. One is just the urgency of the problem that Jeff Sachs laid out in his keynote this morning, and its direct relationship to climate change. But the other is just the economic potential to a follow-up maybe to the dot-com boom of the last 20 years. I mean, is it possible for us to imagine, an energy boom of the next 25 years where all of the work that's being done, all of the incredible ideas that we're seeing presented at this conference, to actually take hold, where people are making breakthrough discoveries, and where these technologies really do start to not only solve a kind of climate and global problem, but also have the economic viability and start addressing some of these problems and questions that we have about how much does it cost. So the presenters in the final panel are part of this next wave of researchers and thinkers. Their work crosses professional boundaries between academia and industry. They crosses disciplinary boundaries between architecture, engineering, computation, physics, just to name a few. And important for the architecture discipline is that their work is grounded and it's located in architecture schools. And this is an indication, I think, that this is the issues that we're talking about today are not only just technological and scientific issues, but also design issues. And that's where I think the role of architecture comes into play. I'm going to now introduce the three panelists all together and then let them just come up one after another just to kind of save time. So the first panelist is Anna Dyson. Anna is a professor at School of Architecture at Rensselaer Polytechnic Institute, and she's a founding director of the Center of Architecture Science and Ecology, known as CASE. Is a research collaborative here in New York between RPI and SOM. CASE is, in my opinion, in some ways unique, certainly within architecture schools in this country, in that it bridges multiple industries and disciplines to accelerate the transfer of scientific discoveries into the design of next-generation architectural systems capable of harnessing local ecological energy. Anna's currently doing research funded by the National Science Foundation, the U.S. Department of Energy, the New York State Energy Research and Development Authority, and the New York Foundation for Science, Technology, and Innovation. Following Anna, Forrest Meggers will speak. Forrest recently was appointed assistant professor at the School of Architecture and the Andlinger Center for Energy and Environment at Princeton University. I think it's interesting in the discussion of where education is going, as this was a joint appointment between architecture and the Andlinger Center. He has degrees in mechanical environmental engineering from the University of Iowa and a PhD in architecture from the ETH. His areas of research are many and include the design and integration of sustainable building materials and systems, renewable energy, geothermal, seasonal energy storage, low-temp hybrid solar, and exergy analysis and thermodynamics. And then finally, Judit Kimpian will speak. Judit is the director of the Sustainable Architecture and Research Group at Aedas Architects in London. And she is one of the founders and project managers at Carbon Buzz. Carbon Buzz is an online platform for tracking energy use from design through operation with the goal of reducing the gap between projected and actual energy usage. She also chairs the Architects Council of Europe's Sustainability Work Group. She has a PhD in architecture from the Royal College of Art in London. So with that, Anna?
I thought I'd start with this slide following the introduction by Dean Wigley about the decline in funding for science and technology being a form of suicide at this point. And I couldn't stress that more. I think the theme of collective suicide has been sort of omnipresent in many of today's discussions. In various fashions, and I could just say that really it is true that it's a tiny, tiny drop in the bucket. If you look at it in the context of the first keynote presentation by Jeffrey Sachs this morning, the amount of funding that is currently allocated or has been allocated in the past, recent past, to clean energy technologies or transitioning our built environment. We saw that pie chart just now by Thomas. We're 1/3 in this country of energy consumption profile of the nation, which is massive, given what we need to do with that energy. So we really don't need to use fossil fuels. So for us at CASE, we really depend on these kind of dribs and drabs, and we have depended on them. And really, part of this sequestration and the shutdown and everything are, in a sense, that these very, very futile, in a sense, shavings off of what are just tiny drops in the bucket for the overall budget of the administration of our country. And if you look at what happens in terms of where that invested money goes in terms of generating economy for our economy and for the global economy in general, it's disproportionately productive, and it's been proven to be disproportionately productive. So it is a kind of suicide move. So with that said, I would say we do have to figure out, in a sense, how to have new relationships with industry, because it's really not going to come probably in the near future from our government. And the decisions probably will not be top-down in terms of how we transition. So how do we capture the imagination? How do we transition certain things? And why would we do it? Would we do it for moral reasons? Would we do it for aesthetic reasons? Would we do it for economic reasons? Probably all of the above, and maybe none of those are necessarily going to be the drivers. But certainly, it seems irrefutable that we're going to have to think, at least in terms of built environments, of how to transition our built ecologies. So that's a specific term that looks at all of our energy flows. I would say I would totally agree with the recent presentation, the last presentation that challenges us to consider our built environment from the standpoint of the flows and the redirection of flows. to start with that, and then to actually transition from concentrated energy from fossil fuels towards the capture, transformation, and redirection of ambient distributed energy resources. And this sounds like potentially old news, right? We've been hearing this for a long time, that it's possible. You know, we've had lots of popular figures such as Al Gore tell us the technology is there, we can do it. Or we've had other voices saying if the political and social will was there, we could do it. And if that were true, there would be many municipalities or even governments, such as Germany, off the grid by now. When in reality, if you look at the carbon footprint of Germany, it has actually increased in the last few years, despite tremendous collective social and political will to move towards clean renewables. And the question is, why? Why have these technologies failed? And how do we feel that we could actually position viable technologies for the future? So I'm going to start by a sort of leap towards what I think is the sort of middle future, maybe 10, 20, 30 years from now. And I'm going to end, hopefully if I have time, I'm going to skip through a bunch of slides because I think we have half the time that was allotted to us initially. So I apologize, but I'll go very quickly through some of the slides and maybe not show all of them. But ultimately, in the middle future, we're living in a pretty exciting moment right now because we have supercomputers, we have tremendous knowledge about the about so-called biotic systems and through genome sequencing and how we might be able to build and construct matter through biological processes. And we also have the ability to look at material processes at multiple scales simultaneously and to design at those scales simultaneously. So that is really exciting for us because if we can cross-link and if we can sort of manipulate energy flows at the atomic scale in terms of the control of molecular and atomic behaviors, and then look at how we synergize that with macro-scale behaviors, then we will have many more handles with which to manipulate energy flow in our built environments. And we have technologies that are emerging today that already do that. For instance, from Lawrence National Berkeley Lab, they have an incredible new technology that can separate, for instance, the visible transmission from the solar heat gain coefficient on glass. So, for example, your windows will behave differently relative to their optical and mechanical properties, so and radiant properties. So this is very exciting. How are we going to move forward with many more handles than just those two examples? So that's sort of the midterm. But in reality, we have a built environment, and these just happen to be morphological squares, I was like patterns from a solar system that I'm going to show you. In reality, what we've done in the past and how we've designed most of our systems is we've designed material behaviors at the material scale, we've applied them to devices, we've integrated them into integrated systems that may be single function systems that are then not integrated with each other. So we have a tremendous dissonance in terms of how we manipulate material in order to process or metabolize energy. And we also have tremendous inefficiencies, even though the legacy from our sort of very long trajectory of burning first biomass, fossil fuels to make things and to manipulate our environments, we have essentially come mentally to be very influenced by what fossil fuels have done for us. So that is, in a sense, we visualize, and we're very interested at CASE in how our mentalities get shifted by the technologies that we adopt, and how much we have come to just assume that we can beam count or process or count energy in buildings or built environments in the same way that we did steam engines, for example. And so we're firmly, in a sense, mentally embedded within the mechanical and electrical paradigms that is our recent past. But in reality, we really need to be thinking about these things very differently and in terms of ecological extended boundaries and open-ended problems. And ultimately, it is true that the closed-loop ecologies, for instance, that we saw being studied on Mars and in other extraterrestrial environments are tremendously instructive for us because they can be reduced in terms of problem sets in ways that terrestrial ecological problems have been very difficult to reduce. So looking at the very, very distant past, and I thought I'd start with our very distant ancestor who's a survivor. And the question is, are we survivors? And what kind of environment are we surviving in? As has been well pointed out, we've been living by burning things for a long time. But the question is, what has that done also to our evolution, not just socio-cognitively in terms of the way we think about things, but also in terms of the way we expect and interact with our environment. And one could just think about thermodynamics as one aspect of that, but certainly sound, light, et cetera, are all part of that. There's tremendous information also that will be very helpful to us. We can see that the structure of our brain actually changes depending from neuroimaging, depending on the thermal environment within which we live. And it happens over time, and there is also very immediate chemical changes also to our processing, our cognitive processing, in terms of what we're understanding about our environment. And so I'm going to skip through some of these slides just to say that one of the basic hypotheses that I have is that we have in the past and today in New York City are in a direct trajectory really from our fire burning past, and really the fire continues, but as one of our favorite theorists would say, Fernandez Galeano tells us we've exiled the fire. And I love those images that were shown at the beginning of today by our colleague Kate Orff of these plants, these massive physical plants that have been exiled to places where we don't want to see them. But in reality, the fire here is 11,000 megawatts per day, basically a kind of converted bonfire into various forms of energy. And everything that we have in our built environment is dependent on that. And that's been well established, I think. But I think that we have to also think about how do we look at that and how do we understand it, even as an aesthetic condition. That is this a beautiful image? It could be. It could be this kind of disaster porn image where it's just so incredible that we've transformed our environment, our globe to this degree in terms of the burning of fire and then its conversion to electricity and so-called light pollution. We could think even about the light pollution as a potential source to be scavenged in the future for energetic purposes. But in reality, there's a condition here, and we have to decide how we want to look at that and what that means. So is it aesthetic to be gestating our material environments and our energetic environments in the way that we do? This is what that image just now looks like on the ground. And one of the things we'll notice about this image, depending on where you are, is this tremendous boundary condition drawn between so-called built and natural systems. We have spent not just the last several millennia learning how to control fire in tremendous ways and control heat processes for the purposes of manufacturing or transportation or living. We've also thought that we could actually exile so-called biotic processes that are extra to our biology. And what I will show, I'm going to skip over these, I think people know about all this. What we will see is that the sort of loss of biodiversity is, of course, an after effect of the way that we've chosen to develop. But in addition to that, the connection between our well-being and our socio-cognitive processes and everything in biodiversity is intimately connected, and we now start to get those feedback loops. So this issue of how we process water, how we process energy, our connection to the food chain is intimately connected. And now, yes, the low-hanging fruit, we would never say that it's wrong to conserve, but it surely can't be a plan for the future. Not the grand plan, anyway. It's good that we will, reduce, but in reality, if we look at the kind of time frames that were presented to us this morning, the burgeoning global development, the emerging global development, we don't really have time to fiddle around and conserve more energy as the plan. If that's the grand plan of the Department of Energy, and by the way, it was with their first major investment in building science, which was the Energy Hub, they are they are developing wireless technologies to detect leaks in HVAC systems, and that's great. But the question is, what should our research project be? What is our basically our CERN moment, if that was like the particle accelerator for physics? What is the CERN of the built environment? What is our most pressing and important problem, and where should we mobilize our resources in order to transition our built environment? And I just use this as a nostalgic slide because I'm too terrified to put the environment that we have today, the very deep floor plate buildings. This was actually the last time, and in 1961, the building codes had transitioned in New York City, but this is really a reflection of the requirement for light and air in buildings. So those were technically still potentially operating in concert with bioclimatic flows. So what about the future? What does the future look like? And we would say that the future is very bright, very complex, very green, regardless of what we choose to do. We could, wow, I've got 5 minutes, so this is like just the preamble. So anyway, we can choose to stick around or not. So how might we do that? We like to fantasize about various ways of offering that, and I think I will zoom immediately to what I think is what we can do today. So we're going to shift from concentrated, centralized forms of energy towards the management of distributed flows, and it's been said that the microgrid is going to be critical for this. We'll shift from bean counting mechanical and electrical efficiencies on individual systems and functions. They will be important efficiency, of course, but what we're really interested in is embedded and integrated ecological effectiveness, multifunctional interdependencies. And so the provocative question is, what if today's built ecologies fostered biodiversity rather than degrading it? What happens? How do we bring our buildings back in concert with not just climatic flows, which are fluctuating, but with the fluctuating demands and the tension between individual and collective desires? What do we really need to do here? In fact, buildings are very low-hanging fruit. I'm going to skip over these things. Buildings are very, very low-hanging fruit in comparison to, and the built environment in general, in comparison to those two other sectors. Jonathan this morning explained why we might have to burn something to fly a plane for time to come, but we maybe can do it much more effectively through biofuels. But let's say if we have to actually take flows that are distributed and then redistribute them, the built environment is a good place to do it because a lot of what we have to do is just, in a sense, transforming the flow of energy, storing it long enough, and then redistribute it through the system to do certain things. And we've got a lot of flows to work with in the built environment relative to what we have to do with them. And so let's say on-site net zero, water management, biocompatible material cycle, restored urban biodiversity, and air quality are synergistic goals. One of the key things, we've talked a lot about thermodynamics today, and we would say that it's absolutely critical that we also transition from a singular focus on thinking about building envelopes or barriers in terms of the conservation of energy, and to think and to shift, because we do that very poorly, as we can see here, with how we try to keep climate out, or we fantasize that we're offloading it when we're just sinking it into the urban heat island many times, et cetera. And shift towards thinking about building envelopes and interfaces as transfer functions, so that we wouldn't waste any bioclimatic flows, not even pollution. Believe it or not, it will actually, Jonathan showed us this morning, is how pollution can be considered an energetic resource for certain types of organisms and also for certain processes. So if we think about solar, moisture, thermal, wind, if we think about capturing them, transforming them, moisture in the air, low-grade thermal energy that lingers around the building envelope, these have been considered problems. They've been considered unusable. And we would say that actually if you transform the quality of these, you can capture them and you can redistribute them. In very water-stressed climates, for instance, like Mumbai, that are very hot, humid, for 9 months out of the year, they have we have the possibility to capture that humidity from the air and redeliver it for potable water purposes through intelligent hydrogels that are distributed through surfaces, et cetera. The storage is a major issue, and this is why storage is one of the major technological problems that the entire world is working on at this point, both electrical and thermal and chemical. But for instance, if we think back to the salt, the sort of osmosis or forward osmosis project that Jonathan proposed, we can use that salt then for a very nice strategy for both looking at the electrical, thermal, and chemical potentials for the storage of energy on site for the periods that we need to actually redistribute them in. So I'll go back to, if we have time, to the kind of dynamic behavior of nanostructured materials that might be coating our surfaces, et cetera. And we have some lab-scale prototypes at very small scales at this point that are emerging with some exciting properties, and also in our relationships with LBNL. But I think for the purposes of this discussion, I think it's important to say that in the very near future, we can take buildings off-grid dependency. And we can also do much more to close the loop on water cycles, certainly gray water cycles in water-stressed environments. Also, the scale at which a lot of our public infrastructure is existing can be at a very, very large solar farming scale for microgrid delivery. So this intimate connection between this sort of occupant scale, if you will, or this kind of ambient exchange of energy, the zone scale and the building scale is really key. The district scale in terms of peer-to-peer sharing, et cetera, is a very key thing. And I'll show just one system example here of helioptics. And it gets very messy when we look at what we can do today, because, of course, we are, in a sense, in a messy retrofit with concentrated energy systems and fossil fuel systems. So, but this is a dynamic solar facade, which is basically doing that kind of multifunctionality. We saw how if we gang up all of the functions together, we start to get we start to get value equations that add up. It's very key. If you think about anything in biological or ecological systems, you can never reduce any of their parts to one system, even though we're still sort of messily within a mechanical and electrical paradigm. Here, at least, we are synergistic in terms of the functions. So this is both a daylighting facade. This is a system that intercepts effectively all of the direct solar energy, the solar heat gain, so reducing the cooling loads, concentrating that form of energy, and then redistributing it for grid power, not grid power, for independence of the building envelope. And so it's this relationship between the thermodynamic behavior of the building and the transformation of energy flows of the building envelope in association with very high efficiency solar cells, et cetera, that start to give you value equations that add up. Certainly the direct current transfer to solid state lighting, all these sort of minimization of transmission losses, et cetera, are very important. So we associate water purification, daylighting, photovoltaic, solar thermal into a combined system. And you can see that this diagram shows, at least conceptually, the idea of trying to close the loop as much as possible between both the active and the ambient, in a sense, degrading. This is a very complex and messy diagram, but I'll just show this as a kind of example relative to the last presentation. So if we're basically transforming at the facade the solar energy, and we can operate very high efficiency solar cells at 180 C and on down, and we're basically capturing and transferring and storing and redistributing that heat for doing work, we basically have a lot to work with in terms of the differentials. And we are looking we have many industrial partners that we work with. We work with Thermocore, for example, to transfer heat pipe technology from aerospace applications, and actually it's already in terrestrial applications in submarines, for example, and combined heat and power. But basically looking at all of the different things that we could do with that. So we're just as interested, to be honest, at these sort of end cycle things where we're just putting things into, let's say, radiant structural members or other things, and then sort of closing the loop in terms of really looking at what do we have to do in terms of a building. So if you think about just one day in New York City, you might shift from heating degree to cooling degree and back to heating degree within one day. You have very variable ambient lighting needs. And the light and the heat, the solar energy is never coming into your building envelope in the form that you would like it to. In general, it's either too hot, it's too bright, it's in the wrong direction, it's upsetting the mean radiant temperature of the room, it's upsetting the light contrast ratio, et cetera. So these are, some of them are social questions, some of them are psychological. In terms of what our expectations are for homogeneity and uniformity and egalitarian access in social spaces, et cetera. But in general, we, not just because the energy is not hitting our building in sort of the forms that we would like it to, it's also, we can stretch it much further if we capture it immediately as it hits the building envelope. So we also have a lot of low-hanging fruit and messy stuff in terms of the existing mechanical systems that we have and that we can work with, but in the past we have not used on buildings because they've been considered so-called inefficient. And what we will say that, once again, this goes back to this sort of ecological effectiveness. If we have energy sources and we can use them, so in this case we might put heat into absorption, refrigeration, cooling, but then the outlet temperature might go into other applications like an organic Rankine cycle to bump up our electrical production if we need it, or if we don't need more electricity at that time of the day, then it might go to something else, like domestic hot water for cleaning, et cetera. So there's a lot of different, buildings are never in the shape we need them to do as well. And just to remind everybody, we're not really talking about new buildings in the future for changing the energy consumption profile of our built environment. It's mostly going to be a retrofit condition. These happen to be retrofits, and in this case, you can see the highest value for this sort of desert climate is really taking the heat out of the space and having a view to the kind of clear daylight of the sky. And this is just for those of you that are interested in the numbers. This is probably it's a best case scenario in terms of climate because this happens to be in Middle California with a great climate. And a very good direct solar climate in terms of the amount of sun that we can capture. But it happens to be a building that has roughly twice the plug loads that you would have for a normal commercial building. So it's a big engineering building. And we are producing 192% of the building load, at twice the plug loads. So this is, and most of the plug loads are not for cooling or lighting or any of those things. So we're talking about a tremendously powerful system if we can capture and transform into high-quality heat and high-efficiency PV. And so the other thing that's interesting about the way that technology sort of emerges is the sort of crazy decisions that our government makes about what they're going to fund and what they're not going to fund. It just so happens that they stopped all funding to LED lighting research because we couldn't compete with China, apparently, in solid-state lighting, whereas in this case, a lot of the fundamental research that went towards green LEDs, as an example, is what we're using to build the indium gallium nitride cells that can operate at 180 C. And of course, in solar farms, centralized solar farms, in the desert, they don't care at what temperature they're operating. That's not a value to them because they're not necessarily going to use that heat for usable purposes because of the way that they're going to transport the energy. So I'm out of time. Oh, sorry, I'm out of time. But maybe I'll just show some videos of some of the projections that so because a lot of in terms of the nanostructuring of materials, our prototypes are very small in the lab scale. So we use also a lot of immersive environments and projections. And in terms of the calculations, I was very encouraged to see Thomas's research because we need much more of this kind of fundamental research in terms of the calculating of what's really happening at the ambient building envelope. I think some of these movies might not be embedded. But in reality, the complexity, the thermodynamic complexity of the building envelope already is extremely complex, even if we did not have dynamically responsive systems. But when we start to actually look at, for instance, taking the data set produced by IBM for 1 mile out sensing weather, for example, and then responding in time with a kind of dynamically responsive system that has to cascade through multiple functions within the building, you're talking about a very, very complex, also computational framework, a virtual framework that would run that. So I don't know where that noise came from. So these are just images of our students that are in our labs upstate, sort of, examining their algorithms that they're that they're sort of producing. This is a sort of a huge charrette that we had, and we did have folks from Bureau Happold and Arup and Norman Foster and a bunch of different firms that we collaborate with or that we're associated with on building projects come and work with us, in this case for a week upstate. For a big charrette, and we got a lot of computation and a lot of experimentation done. And so that's sort of how we work. And then there's test beds that we associate with, various kinds of test beds where we're imagining how we might be dealing with certain urban conditions. This happens to be a transportation hub for Cairo. This is another system that I won't have time to talk about, but just looking at, of course, in our urban environment, we're still going to have tailpipe emissions for a long time to come, and we're going to have very, very compromised air quality in the near future for several decades, probably. And so how do we actually reforestate our cities from within? And how do we amplify, let's say, the air cleaning capacity, for instance, of plants by, in this case, blowing air through the root rhizosphere? So I will just finish with that image because it happens to be related directly to what Jonathan talked about this morning with the Nassau research of closed-loop ecologies. For 2 decades, the biologists were trying to figure out how, in a sense, to create these closed-loop ecologies for space colonization. And I don't think that we would have paid to figure out how to blow air through the rhizosphere and how the bacteria behave, in a sense, for terrestrial problems. So I think these very extreme problems, we have to recognize that they have tremendous value to us in terms of how we're going to transition technology. Thank you.
All right. Thanks, Anna. That was very exciting. I want to come see all these technologies. But unfortunately, I don't have as many pretty pictures for you, but I do have a pretty concept, I hope. I want to take you on a little journey through my path from a very staunch engineer on building energy efficiency to a more enlightened one now, talking about how I go from a place of rejection and no to a place of more knowledge and intelligence when it comes to maybe building systems, and in this case specifically focusing on the idea of developing a low exergy perspective on facades, and hopefully you'll find out what exergy is as we go. So my one full screen image for you, glass, and this is where I started. I started hating this. This is my engineering background. So you look at this giant facade, and as an engineer, you say, man, look, you don't even have to look through this piece of the glass. It's all block, so why did they build this giant piece of glass, which is a terrible performing facade? Why did they do that? And part of that is because, as an engineer, you have some equations in your head, particularly this one about heat transfer. And this is the only one you have to know, and I like to take the equations that Toni uses and try and make them as simple as possible as an engineer, because I'm not a mathematician. And so for this, I want you to understand it, though. So we have heat, and the heat that you have to put into the building then, in this case when you have a glass facade and it's cold outside, is a function of that insulation that you put in it, and the area that you have on the facade, and the temperature difference in that facade. So that drives it, and this is what I look at formerly, I would say, maybe now, as an engineer. Just that simple equation tells me, hey, those numbers are really big. So we're going to have a lot of heat loss in that building. So I have to supply tons of heat to run the building. So this is dumb. So this is the simple perspective. Now, moving forward, in my engineering days, I stood in my engineering silo looking at this glass facade and saying, nah, it doesn't make sense. But then I made a transition. I moved to a place that had a little bit more, where Toni came from, a little bit more integration of people thinking about equations and math and thinking about architecture. And so in this Institute for Technology and Architecture at ETH, we started thinking about what ways can we apply sort of systematic ideas and concepts into the architecture that we're dealing with. And that started by saying, hey, there's something else in that equation that I've sort of forgot as an engineer, which seemed like a relatively constant thing. So I have this temperature part that's driving all that heat flow. And you generally would think, the outside temperature is something I can't really control very much, and the inside temperature is kind of fixed because we need it to be comfortable. So you kind of forget about that part. But actually, temperature is a relatively important thing and plays a big role in how all of our building systems work, which was very well pointed out by Anna in her presentation, showing all these different temperature levels and how cascades of temperature are extremely important in how we run our buildings. So that started this idea of exergy and low exergy integrated systems in buildings. And what that means is taking this concept from thermodynamics, which is an extension of energy, invented in the 50s, but really based on Gibbs' basic laws of thermodynamic potential. And what it is energy you can think of just as a quantity, a measured amount. And exergy extends that, allows us to add a qualitative part about how useful is that energy, which was actually very well described by Jeffrey Sachs this morning when he talked about useful work coming out of energy. So a good analogy then, if we envision me actually only 3 weeks ago arriving from Singapore, bringing my Singapore dollars over here and being like, I want to buy everything in Singapore dollars because they're dollars. A dollar is a dollar, right? Obviously not. This is quite clear. But what's not so obvious to most people is when we talk about energy, 50 kilowatt hours of energy in my electrical grid, 50 kilowatt hours of heat in my boiler, they're both energy. It's the same amount. But when we talk about exergy, actually the amount of useful things I can do with these two amounts is different. I can do more, just like I can do more with 50 US dollars than I can my Singapore dollars, I can do more with the electricity than I can do with the heat in the boiler, even though it's the same amount of energy. So as this is sort of a starting point, we realize that our energy systems are designed with the wrong exchange rate in some sense. We're not thinking about what we can do with all the energy flows that are in our buildings. And thermodynamics can, unfortunately for you, now we're going to get a little technical, thermodynamics can help us out. So in terms of the thermodynamics part, exactly as was said this morning, it's the useful work that matters. And the energy defines this sort of generic quantity, but what exergy does is gives us a definition for that potential, which is equivalent to that quality I mentioned. Now again, here's some fantastic equations for you, but all I really want you to see on this slide is that in terms of heat, there's a part where temperature matters when we do the exergy calculation. And so the equations are just a detailed way of getting you to reinforce this idea that the temperature part matters. It's not just about amounts. So an example that I always use, an analogy which is very useful for my coffee drinking habit, is when you compare this 300 milliliter cup of lukewarm McDonald's coffee to your classic Italian high temperature espresso with 1/10 the volume, obviously there's much more energy because it's 10 times the volume of warm liquid, right? So much more energy. But when we then take into account the temperatures in those systems, actually the espresso has more potential to do work. I could hook an engine up to that and drive more useful energy out of it. Now, this allows me then, of course, to argue that not only do I need high-quality coffee, I also need high-quality exergy coffee, and this drives my rationale now that I'm coming back to the U.S. to say, I can't drink your drip coffee, I have to have espresso, I'm sorry. So, with that in mind, moving back into buildings, and hopefully everybody thinking about coffee is getting energized now. We said you should not have combustion in buildings. It doesn't make sense then for us to heat buildings with a 1,000-degree flame to make a room 20 degrees. We lose 90% of the exergy in that condition. It's not to say the energy part isn't important. We still need to do an energy balance to figure out how much heat we need in the building. So that exact same equation earlier helps us then define, based on the wall insulation, how much energy we need to supply in order to keep the system in balance. This is the first law of thermodynamics. The energy in equals energy out. So we need to know that in order to define the amount that we need. So the energy supply gets fixed, and this is how we design our building systems for the most case. You can get by designing all the buildings that we have today with this methodology because I as an engineer have developed, or not me, but engineers have developed the technologies to put into the buildings and supply that energy. But if we think about the same system now in terms of exergy, that flame that's 1,000 degrees actually is just moving heat into a 20-degree room, and in that case, here we have a 10% efficiency of use of that potential work. So I could have run an engine with that flame, I could have generated electricity with that flame, but instead I put it into a room to make the room 20 degrees. Even in this case where I'm operating a 98% efficient condensing boiler, I'm losing 90% of the exergy in that system. So instead of using combustion, the alternative that we researched and proposed was heat pumps. And the important thing to recognize about heat pumps is that it's not a process where we have an amount of energy stored in our combustion system, or it's not electric resistance where we're just putting electricity in and it turns into energy, it turns into heat. In this case, we're moving heat. So for this case, we're moving heat from outside and moving it inside using a thermodynamic cycle. And by moving it, we can actually move more heat than the amount of electricity we use to do that. So in this case, this coefficient of performance is this ratio of how much heat I can move for every unit of electricity that I put in. And this is very important in these systems because then we start to be able to play with the temperatures, because again, it's the temperature that matters in this equation that determines how much heat I can move into the system with every unit of electricity. So here's exactly, this is why we want to do geothermal boreholes and connect heat pumps into the ground, because we get a better temperature in the ground. And then this also applies to air conditioning systems, or chillers or AC, which are just heat pumps in reverse. And the idea then is we can optimize around this system instead of the traditional paradigm, which is just increasing efficiency by decreasing the amount we need. So we add insulation and we decrease the amount. And we want to think outside of that box and think about where that energy came from. And analogy for this would be, think of the well from whence we pulled this energy. And the depth of that well then represents this part we're sort of missing, the temperature difference that it takes to move the heat from outside to inside the building. So the low exergy building, or the low X building that we developed, was not with combustion, but secondly, and importantly, is also not a passive house. It's not about increasing the insulation, obviously, to a maximum number. It's about having the optimal amount of insulation for the system, not the maximum. So a new paradigm of appropriate temperatures we propose will uncover higher potentials. And an example of that in architecture would be how we're not necessarily just depending on the better glazing or insulation or ventilation systems to decrease the demand, but instead the low X systems can increase performance without having the same design limitations. For example, we can integrate systems and make more high performance facades that increase floor height and decrease wall thickness in some examples. So in this case, getting rid of excess systems that move large amounts of heat around, instead of using a heat pump to intelligently do that. And then when we think about actually increasing the performance of buildings, as would be done in these programs for insulating and increasing buildings, which are very important, it's important for those very old buildings to add just at least a little bit of insulation. But then we start talking about, well, we need very high performance buildings, or we need to meet LEED Platinum standards, or in the case of a passive house, we'll need up to 0.5 meter or 20 inches of insulation to get to that level where you don't need an internal system to provide heat. But now we look at this same wall where we've added all this insulation, and we think about what did that insulation do? It's not a linear system. That last 10 centimeters of insulation, or 4 inches of insulation that we added, did just as much good as the first 1/4 inch that we put on the building. So it's important to think about at what point we have enough, and at what point is the right amount. And a good example that I recently read was in this, for the residential project of the year last year, a passive house building, exactly as I said, 16-inch walls, 24-inch ceiling, but one sentence in the entire article was, with baseboard heating, we were able to cover all the demands just as a backup system for only $200 a year. But for $200 a year, they're doing electric resistance heating, so taking the super high quality electricity that I can do anything with and turning it into heat at 20 degrees. And so then I would say, well, if I could connect a low exergy heat pump system and move 10 units of heat with that same unit of electricity, all of a sudden I would need 10 times less insulation performance in the same building. So then the question becomes, how much did the insulation cost? Could I buy a system? And I'm definitely not saying that passive house isn't a good solution. It's an excellent method to achieve very high performance buildings. But it's important not to, that passive design is used as an effective tool, but not ignoring active systems completely. Now, the case study I want to show you briefly, just to give you one of these counterintuitive examples of how we utilize this concept, is this active low exergy geothermal system that we developed while I was in Zurich. And the idea is sort of counterintuitive in that we take that geothermal energy and we apply it sort of to the outside of the building, not the inside. And the idea is this sort of layer of pipes that sits in the facade of the building on the outside, and it's playing with that exact temperature difference I talked about, because so here you imagine that I have this energy that I'm bringing into the heat pump. So I'm using the ground, which is an excellent temperature, to make a very efficient heat pump, but the heat pump still has to drive heat into the building based on the temperature difference in the facade. So we said, well, why don't we play with that temperature? We can take some of that same really good temperature ground temp, which in general is about 55 degrees. So it's not warm enough, obviously, to directly heat the building, which is why the heat pump is needed. You still have to augment the temperature a little bit. But it's still much warmer than outside in winter when it's 0 degrees out. So why don't we split that up? We can still drive the heat pump, but then we can also minimize this temperature difference across the wall by putting this layer of pipes in the wall. And in essence, creating an effect that the wall feels like it's underground. So we kind of bring that bermed house or earthen house, which would have a very high performance in terms of thermal energy, and raise it up by piping that sort of underground heat into the facade. Now, the performance of such a system that requires obviously some analysis, so we needed at least 2 or 3 centimeters, about an inch of insulation on top of that piping system in order for it to be effective and maintain a uniform temperature. This is important. And then the question we asked once we had the system sort of designed is, what is the equivalent performance in terms of a passive insulation system? So here in the plots are basically different thicknesses of insulation outside, different thicknesses of insulation inside, below the piping, so like the overall thickness of the system. And then plotted on the other axis is the equivalent thickness of the insulation. So you can see as we increase the insulation under the system, these lines are not like 1-to-1 linear. They actually have a slope greater than 1. So every piece of insulation I add, I'm increasing the equivalent amount of insulation I would have had to add in passive, in just plain insulation, by more. So in essence, a 5 centimeter thick system has the same performance as if I had a 12 centimeter thick insulated wall. So in that sense, we can achieve a thinner construction. And on top of that now, because we're using the ground temperature, which is constant, one of the other issues when we're supplying heat to a building is that it changes all the time because the outside temperature is fluctuating. And now we've sort of made this a constant number, and all those machines that have to meet and all those controls that have to meet the changing demand inside the building now can just supply a steady amount of heat and increase the performance of those machines as well. So there's many payoffs that move back and forth between different compartments in the design process. And that's one of the big discoveries we had when working with these kinds of low exergy systems. By playing with temperatures, you end up always working in surfaces, and when you start messing with surfaces, all of a sudden the structural guy gets mad and the architect gets mad. But in the end, when you tell them, oh, we have something that's much thinner and you have less design constraints on how you can make your wall, then they want to be part of the process. And then it sort of develops in a way that's much more collaborative. So this was an example of that kind of system where then again here you see we had 20% less energy when you would make the same thickness wall, so 7 centimeters and 7 centimeters here, the exact same, including all the pumping costs for putting the water into this piping system. So in the end, we have this new product, and it's a novel concept, increased performance. It doesn't have any significant fluctuation in heat demand over the year, which makes the engineers happy. And then in the end, we can say maybe thin can be okay. So it's not so bad to figure out a way to make thin facades. Maybe not. How can we put that into glass then? That's sort of the question you end up being. So this is, though, an example of then when we come back now to the thin facade, there are ways. You don't have to just think about the insulation and the passive performance of such a system. There are ways to be intelligent about how active systems can play a role in the performance of different elements of the building, and especially of architectural elements of the building, which usually engineers would leave alone and architects would keep to themselves. So the question is then, by decreasing that temperature, now am I in love with glass facades? Still not, but I definitely would say I understand them better, and I'm excited to do work on them. In fact, the first project I'm doing at Princeton is to look at this glass cube from 1950 that Labitude built to do solar studies, and now we're going to test it as sort of a space of how can you optimize some of these thin type of structures. So to sort of inform our discussion then, if we can get through this as quickly as possible, my question then is, how can we then better inform our energy decisions? And this goes back to what Dean Wigley was talking about at the beginning. Maybe now, if anything else, at least you understand that exergy has to do with temperature, and for me that's already taking a step in understanding energy better. So maybe by understanding a more complex topic like exergy, you have more appreciation for how complex something that you take for granted day-to-day energy, how complex it actually is in reality. So with that, I thank you very much for the time, and I look very much forward to Judith's presentation.
Thanks very much, Forrest, and thanks everyone for bearing with us. I am aware that I'm standing between you and 28 degrees outside, so I'm going to try and keep this as quick as possible. Many thanks for having me here. It's always lovely to come, and it's great to pick up the contact with Columbia again after 4 or 5 long years. What I'm going to talk to you about today might be slightly controversial, given it's me. And I'm going to tell you a little bit about the work I've been doing about looking at energy consumption for real in buildings. And when the first slide comes up, there it is. Here we go. So I spent probably a good half of my career designing buildings. Oops. Did I just do that? No. Yeah. Oh, back. That's it. Putting interesting things into buildings in terms of a product level, component level, in terms of the form and shape of the building, looking at master plans, and also a lot of the work I've done fed into policy. One of the things I've noticed that as architects, it's quite rare for us to actually go back and look at how well our designs and recommendations have worked in practice. So as Director of Sustainable Architecture and Research, I felt morally obliged to do this and set up a few research projects with University College London, EPSRC, which is a UK educational funding body, to look at things that we found to be real barriers in the practice. The first thing I found that architects, not inside and outside our practice, had real trouble asking good questions from engineers and understanding really where the engineer's work can stop and where the architect's work should start and where these overlaps should really effectively happen. So if you just have a kind of quick scan, I'm not going to go through the details of these projects, but clearly modeling and how we model and what we model and how we track what we've modeled is obviously critical in the age of climate change. What I found was kind of surprising. In the UK, and I know the system is somewhat different in the US, in the UK we have a system called energy performance certification, which relates to both design and operation. Now, what I found that our certificates for design stage are always in the A's and B's and C's at worst. But when I went back to look at the operational rating, which is mandatory for all public buildings above, now it's 500 square meters, all the ratings came out D, E, F, G's, which is slightly worrying. And I realized I was one of the first people to actually do this systematically, which I thought kind of was very strange, because surely if you're after reducing the energy consumption of your building, you must be looking at real energy. It's not virtual energy that we're trying to save, it's the real stuff. So I looked at why this discrepancy happened, and what I found, that what we do for planning, what we calculate for the planning stage of a building, and what we then do for building regulations, what we calculate for the certificates, what we calculate for the different financial incentives, and then what we calculate for the operational certificates and the tax incentives are totally different things. So actually, we're not even comparing apples and pears. It's really a fruit salad. Thanks. I like that slide. So what are we missing? And I think when it comes to energy certification, it's really not the most gripping topic to talk about, and architects are very visual people. So I tried to create a diagram which really sums it up. This is what, oops, I'm back again. This is what we calculate for compliance, a building's performance in very standardized circumstances, operating hours, occupancy, etc. When the building is in operation, then there's the building fabric, which may or may not be what you designed, because the installation may be different, the air tightness is different, the systems may have changed. The IT and appliance loads are not really considered in a way that reflects real-life situations, as we found. Any special functions get excluded, things like external lighting, things like, I don't know, in a school building, you would have training kitchens, you would have furnaces, things that are, as Bill Bordas in the UK would say, the Large Hadron Collider in your basement. The operating hours, as we said, were standard. Most buildings have very variable operating hours. The occupancy, this is a really big subject of debate in the UK because commercial office buildings in particular have very high occupant densities and find that the energy consumption can be quite horrendous. And until we found through one of these evaluations that actually the buildings that have very good facilities management, their operating energy consumption is really not that much higher, whereas the buildings where the facilities management isn't very rigorous, actually the energy consumption from the appliance loads in particular can be horrendous. So if there's a lot more kit in the building and it gets left on for that much longer, that's really a problem. And then the last bit, which I just mentioned, is the facilities management, the way in which a building is being commissioned. All of these areas bring a lot of uncertainty at early design stages. And how can we possibly plan for them up front? Now, to give people a better sense of what buildings really consume, I ended up persuading a few colleagues and professional bodies to set up a platform which Scott's referred to as Carbon Buzz, where you can upload, share, compare the energy consumption of your buildings. You can refine your predictions over time. You can track the consumption of the building, and you can generate easy reports. And the reason why I wanted such a platform wasn't just because I wanted an in-house energy management system that made it easier for me to see what all our buildings were doing. It was because the statistics are actually pointing to some real trends. In this case, education buildings, which we are beginning to have a real high sample size in, show a nearly twofold energy gap. Basically, the operational performance or energy consumption of the building is nearly twice as high as the design predictions, and which is a kind of median figure. In office buildings, this figure is on average 1.5. In the other categories, there aren't that many samples, so it's worth looking at those with a pinch of salt. But that's really quite a staggering figure. What was also interesting for us is there wasn't really a difference between people who were using the standard kind of very simple prediction system or the elaborate and detailed energy models, so the dynamic thermal models. That's interesting because what we're seeing is, in theory, the dynamic energy models would make the prediction more accurate, but what we're finding is consultants are actually using the same presets for a dynamic thermal model. And if anything, the performance gap seems to be a little bit bigger, which means engineers really know how to rig the system. Now, what we can see in the individual categories is if you design a kind of median building in, in schools, universities, or offices, if you had no performance gap, that building would be right in the upper quartile of that building category, which means that we should really worry about this. But given that there are so many things to worry about, we thought it's actually much better to concentrate on things that we can do. So what can I do? As an architect, I can go to my engineer and I can say, give me an energy budget for how my building is going to consume energy. So initially, engineers would give you a rough figure for thermal energy and electrical energy, and you can construct an easy energy bar from that. In this case, this was a UK Carbon Trust-sponsored refurbishment. You could see that the pre-refurb meter, the modeled refurbishment, so this was the existing building, that was the modeled refurbishment, that was the post-refurb, which is higher. The low-carbon refurbishment came out with a higher figure than previously. And then they did a post-calculation showing that actually it could be better. It doesn't really tell you much, so the thing that you do have to ask is what goes on heating, what goes on cooling, what goes on fans, lighting. So how is energy being used in the building, and where is it being used, in what hours, in what zones, and how can you, as a designer, work with your engineers to make sure that your building is actually resilient to those demands in these different end-use areas. And in this case, it's quite easy to tell that the 6 extra cache points that they ended up installing was never calculated, which is fine, but if you're going for a really low carbon performance in use, then you can't miss things like that, because cache machines also have heat gains, they pump up your cooling flows, etc. Another data set was from the Education Funding Agency. A larger body, funding body like that, all they want to know is what's my average performance, what's my worst, and what's my best, and how can we get all our buildings to be here, what are they getting right? And even this level of data capture can give you some very, very good information about where to start breaking down the data into a little bit more detail. I'm kind of proud of this slide because I think we're one of the few practices who've actually bothered to go back and look at all of our flagship buildings that we've recently completed, and we can say that we actually know what these buildings are consuming in operation. And what you'll see is that that's a mechanically ventilated building. That one's a mechanically ventilated building. These are fabric-first design approaches. This is a very complicated building with lots of complicated controls, although it's a naturally ventilated building. And there's a pattern beginning to emerge that all the buildings with lots of complex systems end up going towards the G spectrum. And the buildings that have been designed with very minimal systems tend, and with the fabric-first approach, tend to perform a lot better. In fact, this was one of the buildings that performed better than we calculated. Looking at this in a slight more detail in one of the education buildings, again, you see this was the building regs data. That's the first set of meter readings, second set of meter readings. We can't tell much from that. But as soon as you go into the detail data, you can see that the heating's a hell of a lot more. The ground source heat pumps didn't work. The lighting's about 3 times more. The fan power is more. Cooling loads are more. So we could start looking at the building. Well, what did we not get right? First of all, it was actually quite difficult getting the data out of the building. We did spend about £200,000 on metering on this building, and amazing how many buildings I see where the submeters are not connected, not calibrated, really not rocket science stuff. But if you know that you want data out of a building, then the submeters do get connected and do get calibrated, and they give you really useful information about where energy is being used in the building. These are all the little meters that you have to then read by hand, which is a bit of a pain. AMR data, automated meter readings, half-hourly data that you can get online, in this case told us that the overnight consumption, the baseline consumption was really high in this building. You can get to all sorts of conclusions from just this very simple data. But what was clear is that after a while, after a few questions, that the night purge wasn't working in the building. It wasn't properly configured. In fact, I haven't come across a single building in all the studies of the 14 now buildings that I've seen where seasonal commissioning wasn't somehow value engineered during the contract. So without the night purge and without the proper temperature profiles from the seasonal commissioning, the building ended up opening the windows in all the wrong times and having to use a lot more heating. This is a classic one. On the corridor, a simple lock has been value engineered, or we thought was value engineered. Therefore, all the ground floor doors in this education building were always left open. As it turns out, it was a £2.50 solution to fix it, which only after a week's work did we find out how to, what exactly happened. You just had to show someone how to withdraw that little latch so that the door could open automatically. I can tell you all the press photographs of all low energy buildings, pretty much, respect to the exception, have beautiful internal daylight shots with all the lights always on. In this case, someone forgot to program the zoning onto the lighting system. It was a really, really expensive, excellent lighting system that we had installed. Shame was, a mouse moved in one corner, the whole building lit up like a Christmas tree. Occupant feedback. It's very, very important from an architect's perspective to get a sense of whether these performative aspects of the building reflect upon how people actually feel in the building. In one of those, the Fabric First buildings, the one I was showing before that performed really well, it was amazing to do this survey because people just came up to you and said, oh my God, this building makes me feel human. And you go, what do other buildings make you feel like? So occupant feedback. Another thing that we found is that there's always a big debate whether how architecture relates to building performance and occupant satisfaction. And in the UK in particular, the education minister tends to say very controversially, more controversially than me, that architecture really doesn't matter and we shouldn't spend on it. So that makes architects very angry sometimes. But what we found is where occupants were very happy with the architecture, they are a lot more forgiving with performative issues. That doesn't mean that the building shouldn't perform better, but two buildings where the CO2 readings, the humidity readings, the temperature readings were nearly identical. One of the buildings was very complicated and the users hated it. And the other building where users were really happy with the building, the occupant survey results were drastically different. So there you go, Michael Gove. Read this. I love this diagram because it reminds me of all the grasshopper models that we do as architects. And you wouldn't believe it, this is a building management system diagram. Now, in education buildings, I go back to education buildings a lot because a majority of the studies were done in education buildings. Caretakers are not very complicated people. They are very good, very reliable, lovely people. They don't come with PhDs and engineering degrees and haven't played with grasshopper half their early childhood. So when they look at one of these, they worry. Whereas actually, all it means is that you just have to understand a little bit how these pumps and fans are actually interconnected or interrelated to the temperature set points and the zoning points that you set. But that's not happening most of the time. And in fact, the Building Performance Evaluation Program in the UK that was recently funded by the Technology Strategy Board found that out of the 50 non-domestic buildings, only one had a well-functioning building management system. And this is pretty damning. I don't think it's damning for architects. I think it's damning for all of us. Because these are pretty expensive systems to install. And it does seem that the systems can be smart, but they're only as smart as their users. And if the designers don't commission them properly, if the interfaces, the controls aren't easy to use, then they are not going to be smart at all. And they're going to upset a lot of people. Just to put some figures to this, in terms of capital cost, we invest in an average office building between 20 to 30% in the MEP systems. This mainly relates to supplying and tempering fresh air. When you look at the whole life cost of the same type of building, you would go, okay, that's 85% now. This is beginning to be a lot of money. Are we getting real value out of these? So this is a building where we are designing for a display energy certification of A rating. That means it's really up there. It's one of the best performing buildings that's ever been designed in the UK as an office building. What's different about it is we are targeting operational energy use. So we want to rule out a lot of those uncertainties that I was talking about before. And I begged and pushed and shoved. And the engineers ended up calculating for me all of these areas as little energy budgets. So this is what our appliance load is likely to be. These are going to be all our special functions. The building is going to be actually 9 hours. That we're going to have X number of workstations working in this and this way. And I found that designing buildings in this way actually comes up with less services, and we end up with more resilient systems and designs. And the simple system that we kind of agreed on, which is now being pushed quite broadly now by the RIBA, the Architects Council of Europe, CIPSI benchmarking groups, all these organizations, is to really look at a measured energy use target from upfront. Look at all the parts of the building that will contribute to that performance, and continue to update your energy prediction as those parameters change during the design process. And when you finish the building, go back and recalculate it as it was built and start comparing to what you initially thought it would do. I'm going to show this very briefly. I worked on a lot of tall buildings for a while and became very confused by the amount of time it took to get the coordination to work. On tall buildings in particular, it takes extra long time. All I wanted to do was cycle through some different variations of floor-to-floor height, floor plate depth, whether we have perimeter daylight management or not, what the lighting loads are, what the occupancies, what are the set points, what are the ventilation systems. Do we really need all these loud fans in buildings? One kept me up all night, sorry. I know the US, you're obsessed with fans, honestly. So we came up with this model where an MEP model, an engineering, a mechanical model, was superimposed to a structural model and a quantity surveying model, and you could go and change the shape of the building and change all these other parameters and end up with a pretty good prediction of what the building would be doing in capital cost, whole life cost, etc. So in a BIM model, we tend to send all this information out. The difference is, in this model, all these different knowledge silos were integrated. The trouble is, they're all interconnected, so it took a little while to do the model. I'm sure some of you could do this a lot quicker than I did. But what this type of modeling does, you can type in a target net area and cycle through, and the computer software actually generates your extruded model. And the related quantities, the ratios by which you judge how efficient the systems are, capital cost, whole life cost, operational and embodied carbon. And you just cycle through the iterations and the figures continue to upload. Very quick note, since I haven't got any more time. We were talking about how buildings should be more adaptable. In this case, we designed a building that would normally be a B-rated office building in the center of town, but we designed it with taller floor-to-floor heights and shallower floor plates, so we could adapt the building over time from residential to office and back to residential whenever. It's interesting how the agents are quite resistant to this type of approach, but that ultimately adaptability is really a big deal when it comes to resource consumption. So a quick lesson to close the performance gap: set up your targets properly, then do your modeling properly, and then go back and look at what it ended up being. A very quick note about the EU. Energy efficiency is the largest clean tech market, worth 720 billion globally in 2010 and growing by 10% annually. There was a recent study by the Fraunhofer Institute that 41% energy consumption reduction by efficiency measures, simple efficiency measures, is achievable. And the economic benefits are much greater than often opting for very high-tech solutions. And to say North America, people say that often I think where you are, you think not that much is happening, but actually the US is leading the way in the reporting and publication of data through what's happening in large US cities. So I encourage you to look at the data that's emerging from all these cities collecting their data. And I might finish on that, looking at, that's not working anyway. So the big questions, as Forrest was saying, can we integrate heating, hot water, cooling, ventilation controls, lighting, appliance loads, all of this in the building fabric? We have seen some really interesting approaches to this from the past speakers. And can we design surfaces that light up, walls that breathe and emit heat or absorb cool, ceilings that modulate sound? And is, in the age of super intelligent objects, do we really have to engineer out building management systems to get buildings to operate to expectation? There you go. That's one of our attempts. Thank you.
So I think what we're going to do, in the interest of time, is just have the last two panelists come down here, because we don't have enough chairs.
Yeah, we can just sit on the edge.
And then maybe Craig and I will just ask maybe one question each and get responses, and then give you guys an opportunity to ask questions. So, and and I'll just start. I mean, it's very hard to tie all 6 presentations together, but I am with the last 3 presentations. When Anna and Forrest were presenting, I was thinking, like, what are the obstacles to shifting into this way of thinking, of like really having a fundamental shift of how we think about energy? Like, what is in the way of this actually occurring? And then when Judit presented, and was really dealing very much with what we're doing today. We're trying to implement ways to build more energy efficient buildings, and we're trying to come up with ways to track that usage, and then what you're doing is trying to close that gap. But I guess, and maybe this is an unfair question, but I'm wondering if one of the problems in fundamentally rethinking how we understand energy, if our focus today so much on data, so much on technology, so much on like adding more stuff to a building, is actually interfering with our ability to actually rethink the fundamental question. In other words, if we're kind of internal to our industry, kind of interfering with our ability to actually step back and rethink energy in the way that I think that you guys are thinking about it. So I'll leave that as an open-ended question for anybody. Maybe Craig, if you have a question, then maybe you guys can just respond.
Well, maybe we should respond first to that question.
Okay.
So I think I can build on that.
Okay.
Maybe Juan, you want to
Yeah, anybody can
contribute
use
here, because I think your examples back and forth between those two extremes were interesting.
Well, yes, I think you are right, because the feeling at the end of the day is that we need more interaction between the presentations. No, we have like architecture is trying to do it, and technology is like helping, and I don't like very much this idea of helping, because that means that really architecture is not so changing very much. It's just doing better, but doing the same, with better machines, with more sophisticated systems, with more expensive supplies. I think somebody said, call the engineers, to solve the problems. I think that's exactly what we have to change. We have to work together from the beginning, and architects have to try to obtain some architectural benefits from the questions offered by engineers or by consultants in general, and consultants have to make this effort of understanding that what they are developing, formulas and equations and all these things, have a real presence in terms of changes the space, changes the experience of architecture, and changes the quality, not only in terms of temperature or humidity, the real quality of life, no? I was concerned about how bad is the architecture shown in the images, for example, of the Omega project. No? I'm sorry, but really these general images of the project have very low interest in buildings or low interest in urban organization of this huge map. No? And I was concerned about why you don't call an architect, why engineers don't call architects to do everything they think also, as we do. No? We have, in our presentations, we have, I think, interesting engineer drawings. The engineers usually don't have interesting architectural drawings in their presentations. Why?
I have my architect colleague does all my drawings for me all the time.
It's the end, no? It's the happy end.
Yeah, all the drawings in my presentation were done by an architect, not me.
Yeah, it's sort of hard to know how to answer that. I mean, we're a group of architects, artists, engineers, scientists, and we work together. And it is true that a lot of the images are not produced necessarily by us in terms of the buildings, for instance, that we showed. You know, variously, there was method design, shop architects, SOM, lots of different architects. Images were shown in the presentation, and I think maybe you know, at least in terms of you know, we talk a lot about this sort of dominance of the eye and what things look like, and a lot of times we're interested in maybe suspending judgment with that and maybe thinking more about what do things feel like, you know, other senses rather than the visual, for starters. So the visual is not always the point of departure in terms of the way that we're conveying information. And then secondly, in a response to that, I completely agree with that. What I think the critique is it's not about, you know, an architectural framework and then let's hang some stuff on it. And it's too bad if that's what it looks like. And I would agree that that's highly problematic. We would say that that's very, very much a late 20th century architect's viewpoint of technology, oftentimes. Very, very problematic. And I would say, let's go back to the future, to the mid-20th century or the early 20th century, and think about how historians have actually reviewed figures about like Le Corbusier, like Niuta, like Mies, and how reductive they're of the Oeuvre Complète of Le Corbusier, for example. You couldn't see something that was more synergistic in terms of protagonists and material culture. The Ameses are another good example. They were protagonists in material culture that was very collaborative, and they were reinventing the DNA of how we build. But they were also very, very connected to how, for instance, the overall morphology, like that pyramid that Thomas showed, where the overall morphology and the sort of orientation, the major decisions of the building will have by far the greatest impact on the energy consumption profile of the building in terms of the way that we gestate energy today. But that is not disengaged from the surface treatments or from the technology that's embedded within it. It has to be conceived simultaneously. And the question is, we've become so specialized, so disengaged. I mean, the way that we talk about technology in architectural education, we relegate issues of performance to tech courses and other things, and then we say, okay, let's analyze what we've done and see how it performs. I mean, even think about doing that. Even think about what that means to do something and then analyze the way it performs. Fundamentally, as an example, what Thomas was proposing was to look at architecture from a completely different standpoint. Why wouldn't we actually start to look at it from the standpoint of the engineer and in terms of the standpoint of energy, flows of energy, before we even think about what the physical or visual construct is? You know, how much we find the image beautiful or not beautiful. I mean, these are very culturally ascribed and very biased also viewpoints. And I I would actually suggest, why not suspend the visual for a minute and start to think about the energy flows first, and not even think about what it looks like for the moment. So I would turn that question on its head and say, maybe the architect shouldn't be the one driving the boat all the time. So,
I mean,
I say
I
that
would
as
just
an
comment
architect,
on
you
it
know?
and to ask another question.
Yeah.
I think that, well, I'll talk as an engineer for a second. I mean, we don't like multivariable problems, especially when there are so many variables. And I think energy is that type of issue. Right. It's different than a 20th century structural rationalization problem of of modern design or modernist design. It is a more fundamental problem, and it's a problem that has its nature in looking at different zones of control, whether you're talking about a building, a neighborhood, a country, an ecosystem, and the solutions are very different as you get out. I mean, we've been talking in the afternoon about the building zone, really. I mean, in many ways, which often has at odds with the other zones of neighborhood or density of cities or things of that nature. And I just flip a question on top of that, which is, and to Judith's analysis, which I thought was very on the mark. We find the same exact thing internally to our organization, and many of the predictive EUI models, predictive energy use intensity models that we do during design are not matched. They're not even close. We're 20, 30, 100% over, often in terms of what we can actually look at using. And quite a few U.S. clients that I work with do not actually want us even measuring their buildings. But what we also find is very disconcerting is that even when we are actually looking at energy efficiency in such a way as to do better, more energy efficient forms and building technologies, the energy use intensity continues to grow. I mean, this is just a fundamental issue for me in terms of energy efficiency. And I put this back to you, Judit, in saying I think I saw some patterns of what you were looking at, but in terms of the trajectory of buildings, building use intensity is going up, even though energy efficiency measures are getting stronger and stronger. So could you comment on that?
I think what you're saying actually is leading to an interesting point, which is, should we regulate or not? Is it about regulation? And I do dedicate quite a lot of time to this Architects Council of Europe role, because I firmly believe that we must legislate. It's really the number one is because one of the biggest impediments is that, I mean, you've seen from the Carbon Bus project, it's actually really difficult to see how well you're doing with your design and with the operation of your building, because the metrics are so different in different stages of design, and because they're so different amongst different countries. So you can't compare a building designed in Sicily to a building designed in Denmark, whereas actually you're really just talking about kilowatt hours. So what's the fuss? And so my big campaign line is to harmonize the reporting metrics. You don't have to harmonize the rating systems. You just have to harmonize how you report and what you report, so you can actually tell whether what you're designing is any good and whether you can learn from other people who have done it better. Because and in the absence of regulation, it's only vanity that can drive this forward. And I think vanity is not strong enough unless there's a business case attached to it. And what we're actually finding now is that there is a very strong business case, and it's not just the energy price, but we have found that when you're looking at energy, not just in terms of the operational energy use of the building, but also in terms of the embodied energy of the building, what amount of effort goes into making that building. We're finding, so when we do embodied carbon, embodied energy calculations, we find enormous amounts of waste that financial assessments do not bring to the foreground. We just don't notice what amount of waste is going on. And I think energy is, it doesn't solve everything. Doing a low energy building isn't going to make a beautiful building, but it might help you focus on areas that are totally wasteful, because you're simply looking at how much effort is going into making that building and in keeping it comfortable and bright and habitable. So I think an awareness of architects of where energy is in a building, how much of it went into making it work is really essential. And it's this literacy is something that I think we have to ingrain in the you guys, next generation of architects. And I wish someone had done for me and made it look interesting enough when I was a bit younger.
I mean, are these externalities able to, I mean, you talk about externalities, but maybe, Janet, you could comment on that, because, I mean, you're talking about a lot of this issue within the Underdome project in terms of, I mean, when I look at that information, I see problems that you just can't even solve. And so is it possible to track all those externalities to get to a true equation? I mean, to the type of things that Toni was referring to.
Yeah, it's true. It's I think I don't know if this is on, but one of the problems of dealing with externalities is that the problem gets sort of insurmountable. That in a way it becomes too big to deal with, and I think it makes sense that people try to avoid that big picture for that reason. But I guess also going back a bit to Scott's question, I think one of the things that has interested me in the discussion today has been to see ways in which every one of us is basically framing the energy question around a set of variables or a set of interests that are, I think, different or broader than the ones that we have been talking about for the past X number of years. And I don't know, I'm so struck on, Anna, with your comment that, you know, if we're just pushing heat out of buildings, we're just contributing to the heat island effect. I love that comment because it just points to that idea that you just need to zoom out a bit, that in a way you can't sort of just focus on the building as this kind of net zero skin or this kind of net zero enclosure, but that you see this bigger field. And yes, that is the field that includes these externalities. And then what do we do? You know, I think that's the question and the problem. And it does seem like if you focus on technologies alone, there's a tendency to avoid those bigger questions, those difficult questions. But I think maybe what our task is, and I think what we're all doing, is to understand the meaning behind those technologies, to understand that there are decisions behind each metric. There's a question about, you know, what efficiencies you're trying to gain and sort of when to let up and and just let things happen. And I mean, that I think is where this question gets interesting, and that's where the kind of politics are always at play in the technique, the technology.
Yeah, and well, in reference to the how the technologies then play out in the in the original comment about how we get engineers and architects to work together. I mean, I think what I presented is the most complex version of what I would ever present in architecture school, and is that it's more like an instigation to get people and thinking about the fact that there are so many levels that can be explored in terms of what the impacts are of using of this idea of energy moving throughout the systems from the urban heat island effect. I mean, it plays out across every different aspect of our lives. And what I showed was a tool that maybe gives a sort of perspective on the technological side, but when we implement that, and all the experiences I've had over the last almost 10 years of trying to teach exergy sort of concepts to architects, is that in the end, they may not be experts in thermodynamics, but all of a sudden their interest in using the concept, the conceptual part of it, not the equations. I mean, we showed that, but the part of doing that in the process, even at the beginning of their designs, we found in Zurich, the students would come to us at the beginning of the semester, not at the end with their designs. They would be like, well, how is it possible to use geothermal in this site that I have at the beginning? Instead of at the end, we're like, can you help me figure out how much energy my building that I already have designed uses? So I think this is sort of the change in the pedagogical aspect of the architecture is creating a dialogue that's fun for the architect, where they can bring it into the conceptual framework. Because as engineers, we learn analytical methods only. You learn how to be an analytical thinker and a problem solver based on fundamental laws of nature. And as an architect, you learn to be a designer that thinks from concepts and brings them down to an application level. And I think that meeting point between engineers and architects has diverged over the last years, and now it's time to bring it back together. I think that's where you'll have more productive and more interesting things coming out, and that will be where we start to see energy happen in architecture, I think.
Gavin, are we out of time, or do we have one question? Okay.
Thank have one question, but it's maybe for a number of people. Well, it's not one question, but it's for a number of people here. And that is, I was very intrigued, Anna, by what you were saying about energy from buildings. And I'm curious, I'd like to get input from anyone on the panel, the extended panel, about harvesting, looking at buildings as a source of energy. So, for example, piezoelectrics. Buildings are going through, particularly large buildings, are going through massive stresses because of windage and effects of various things, heating and cooling. We don't take advantage of the gradient. We think of how we're going to limit the gradient, but could we take advantage of the gradient? Could we take advantage by piezoelectrics of the stresses that the building is producing? And do we have to think about the whole building all the time? Can we isolate parts of the building and use isolated parts of the building to control other parts of the building? Using biological metaphors, like we sweat when we want to cool ourselves and we shiver when we want to be warm, and clearly you can't get a building to shiver, but you understand what I mean. There are ways that we can think of the biology that teach us about how the system could work and how the building could be thought of as a source of energy from the get-go. We build into it these sort of structural elements that allow us to harvest energy because we built this enormous structure that's incredibly heavy and has got all kinds of sail stresses and so on and so on. I don't know if any of you would...
Well, I would just say first, historically that wasn't part of the process, and now I hope it will be, to sort of follow up on what I was just saying, is that I think it's difficult to do that now in the process we have. How do you make these piezo things in the building when the building's already designed and done? So that's kind of the...
Actually, that's a really good question. It's a really good analogy because, and I love the fact that you're using biological analogies and then alluding to piezoelectrics, because it gets rid of this dichotomy that doesn't really help us very much in transitioning, because we're sort of, we have things at our disposal like piezoelectrics, and so we can make the building shiver in order to change the heat transfer properties of the building envelope. And we can retrofit building envelopes with piezoelectrics in order to do that, because we can transfer, because that's exactly what we do on bluff bodies in aerospace. In airplanes, for example, in aeronautics, we embed piezoelectric flow control jets, synthetic jets, very inexpensive technology, in order to control the flow. And what we're doing when we're shivering is we're basically just creating more turbulence at our skin in order to insulate our body more. And that's exactly what we can do on building envelopes today. That is very low-hanging fruit because it's inexpensive technology and it's already been demonstrated in aeronautics. So, and I don't mind saying that we actually are demonstrating that in the wind tunnels now, and potentially will work with SOM to retrofit a building with that technology. So hopefully quite soon. And so those types of things are really great analogies. We can create a lot of, there's so many biological analogies that can help us in terms of just, changing certain dynamic behaviors that are already in place and embedded within urban airflow, for example, in that case.
I mean, but just to say the realities of the situation, there are technologies even acceptable. Anna's types of technologies she's really perfecting in lab and scalable senses, they're there, but we're faced with an externality issue in terms of energy is cheap. It's 8 cents a kilowatt hour, and while it stays there, and while carbon is not priced, and while that problem exists that Jeffrey posed to us, we are going to be really stuck. We're going to be fundamentally stuck because it will not pay out.
We've spent a lot of time talking about how expensive energy really is because of externalities that are not acknowledged. But I agree with you in terms of dollars and cents. It's true that it's cheap. In terms of just common sense, it's totally expensive not to think in these terms.
I agree with that.
I wanted to follow up with a question for Judith. Anna and I yesterday were talking about the metagenomic of buildings. It was kind of an interesting idea. We were talking about the microbiome, the sick building syndrome, fungi and bacteria and all that stuff. Do you evaluate buildings on those terms as well?
There's a really interesting study that's just been done by this wonderful lady at UCL who's looked at a lot of the education buildings that we've been studying for sick building syndrome and incidence of asthma and learning and days of sickness and all those things. And she's found some really super stuff, which is, for example, when you have floor vents, if you distribute air from the floor, and if you have a certain type of carpet, the combination of the two, I mean, this should be headline news, really. It's really very bad for kids. It's very bad for adults. It should not really be done. And because basically all the stuff that goes on the floor, it gets blown back up into the air. So she's done, I can send you a link to her PhD thesis, which is really interesting and really thorough. There's a lot of debate about passive house. I've always been a bit, I love passive house, and I think it's one of the best systems to get a very low performance gap when it comes to the heating energy of buildings. But I don't think it takes, for example, summertime comfort into account. Like I went to see a friend of mine in the summer heat, and passive house buildings have low ceilings because of the amount of volume, the perimeter that you just don't want to expose too much perimeter, because you won't pass passive house otherwise. And of course that you lose the stratification then in the summer. So and the light building fabric doesn't give you the thermal mass that the nice traditional old buildings give you. So there is also, and then when you then turn on the fan in the winter, if you don't clean the filters properly, very few filters are properly maintained in ventilation systems, then you just end up blowing things back into the air that isn't.
What animals do is they have a winter coat and a summer coat. Anyway, thank you for your.
We're going to take maybe 5 minutes, a 5-minute break, and then we're going to come back for Matthias Schuler's closing keynote address. Thank everybody on the panel.
Thank you.